Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the faint glow of the Milky Way. But here's the thing. Every single speck of light out there is part of an epic story, a cosmic saga written over billions of years. And tonight, we're diving deep into that story. Welcome to 40 Cosmic Milestones in the Evolution of Galaxies, where we'll unravel the universe's greatest hits, the moments that shaped everything from the first flickers of starlight to the sprawling galactic cities we see today. Think of it like flipping through a family album, except this one stretches across 13.8 billion years, and the family members are galaxies, each with their own dramatic tales of birth, growth, and transformation. What's wild is how much we've pieced together in just the last century. 100 years ago, we didn't even know other galaxies existed beyond our own. Now, we've traced their evolution back to the cosmic dark ages, when the universe was a fog of hydrogen gas, waiting for gravity to work its magic. And the milestones we'll explore, oh, they're mind-blowing. Picture the first galaxies, tiny and fragile, igniting in the darkness. Imagine colossal collisions where galaxies merge like titans, reshaping entire regions of space. And then there's the mystery of dark matter, an invisible force weaving galaxies into the vast cosmic web we see today. This isn't just science, it's the ultimate origin story, and it's happening all around us if you know where to look. So why does this matter? Because every time we uncover one of these milestones, it's like finding a missing puzzle piece to the biggest picture there is, our place in the universe. Galaxies aren't just pretty swirls of light, they're the engines of creation, forging the elements that make up planets, life, even you, and the wildest part. This story isn't over. Galaxies are still evolving, still growing, still hiding secrets we've only begun to guess at. So buckle up. Over the next video duration, we're traveling across time and space, from the universe's first whispers to the galactic giants of today. And trust me, you won't believe how far we've come. The universe wasn't always filled with glittering galaxies. It all started with a bang. Not just any bang, but the Big Bang, a fireball of energy so intense that it set the stage for everything to come. In those first fleeting moments, the cosmos was a seething cauldron of particles, hotter and denser than anything we can imagine. But hidden in that chaos were tiny ripples, quantum fluctuations, minuscule wrinkles in the fabric of space-time itself. Think of it like tossing a handful of pebbles into a still pond. Those ripples might seem insignificant at first, but given enough time and space, they grow into waves that shape the entire surface. And that's exactly what happened here. Over billions of years, gravity got to work, tugging at those faint wrinkles, pulling matter together bit by bit. Regions that were slightly denser attracted more gas, more dust, until they became the seeds of the first galaxies. It's almost poetic. The largest structures in the universe owe their existence to the tiniest of beginnings. But how do we even know this? Enter the cosmic microwave background, or CMB, the afterglow of the Big Bang. Picture it as the universe's baby photo, a snapshot taken when it was just 380,000 years old. This faint glow, detected by satellites like Planck and WMAP, carries imprints of those primordial ripples. Scientists analyze these patterns like detectives deciphering fingerprints, uncovering clues about how galaxies began. Without those initial fluctuations, the cosmos would have been a smooth, featureless sea of gas, no stars, no galaxies, no us. What's even more astonishing is how precise those early conditions had to be. If the ripples had been too weak, matter would never have clumped together. too strong, and the universe might have collapsed back on itself before galaxies could form. It's a cosmic balancing act, a delicate tuning that allowed galaxies and ultimately life to emerge. So the next time you gaze up at the night sky, remember, you're not just seeing stars. You're witnessing the legacy of those first whispers of structure, the echoes of a moment when the universe was just learning how to build. For nearly 100 million years after the Big Bang, the universe was a cold, dark place, an endless sea of hydrogen and helium gas with no stars to pierce the gloom. Scientists call this the Cosmic Dark Ages, and it was during this silent stretch that something extraordinary began. Deep within those primordial gas clouds, gravity worked its slow magic, pulling matter together until pockets became so dense, so hot, that nuclear fusion sparked to life. And just like that, the first stars were born. These weren't like the stars we know today. Imagine celestial behemoths hundreds of times more massive than our sun, blazing with a ferocious blue-white light. They burned fast and died young, their lifetimes measured in mere millions of years, a cosmic blink compared to stars like our sun, which shine for billions. But in that short time, they changed everything. Inside their cores, hydrogen atoms smashed together, forging heavier elements like carbon, oxygen, and nitrogen for the very first time. This was the universe's first chemistry lab, cooking up the ingredients that would later become planets, oceans, and even life itself. Then came the fireworks. When these giant stars exhausted their fuel, they didn't fade quietly. They went out in titanic explosions called supernova, scattering their newly forged elements across space like cosmic shrapnel. These explosions did more than just light up the darkness. They seeded the universe with the raw materials for everything that followed. Future stars would form from this enriched gas, their planets carrying traces of those first fleeting giants. This era, known as Cosmic Dawn, wasn't just about light, it was about transformation. Those early stars acted like cosmic alchemists, turning simple gases into the building blocks of complexity. Without their fiery lives and violent deaths, galaxies would have remained barren, lacking the diversity of elements needed to create rocky worlds or organic molecules. It's humbling to think that the iron in your blood, the calcium in your bones, even the oxygen you breathe, all of it was forged in the hearts of stars that died before Earth even existed. And here's the kicker, we're still finding echoes of that first starlight. Telescopes like the James Webb Space Telescope are now peering back to this pivotal era, capturing the faint glow of those early stars as it stretched across billions of years. Each observation is like unearthing a fossil from the universe's childhood, helping us piece together how we went from darkness to a sky filled with light. So the next time you look up at the stars, remember, you're not just seeing points of light, you're seeing the legacy of those first, fearless pioneers that lit up the cosmos. Those first stars didn't just shine alone, they became the anchors for something far grander. As gravity continued its relentless work, it pulled together not just stars, but vast clouds of gas and dark matter, creating the universe's first building blocks of structure, Proto-Galaxies. Picture these as cosmic toddlers, clumsy, chaotic, and full of raw potential. They were nothing like the elegant spirals or smooth ellipticals we see today. Instead, they were turbulent, messy blobs, swirling with gas so thick it blotted out light, seeded with the heavy elements from those early supernovae. What made proto-galaxies so special was their role as galactic nurseries. Inside these dense clumps, conditions were perfect for birthing new generations of stars at a staggering rate. But it wasn't a peaceful process. Imagine a construction site where bulldozers are constantly crashing into each other. That's how violent proto-galactic growth could be. Collisions between gas clouds triggered shock waves, compressing material and igniting bursts of star formation. Meanwhile, dark matter, the invisible scaffolding of the cosmos, wrapped around these structures, providing the gravitational glue to hold everything together. Here's where things get even wilder. We can actually see this era thanks to cosmic time machines. Quasars, the brilliant cores of distant galaxies, act like lighthouses piercing through the early universe. Their light passes through proto-galactic gas clouds on its way to us, leaving behind fingerprints in the form of absorption lines. By studying these patterns, astronomers can map the distribution of gas, uncovering how proto-galaxies grew and merged. It's like finding shadows cast by invisible structures billions of years ago. And those mergers, they weren't just side notes, they were the driving force behind galactic evolution. When two proto-galaxies smashed together, their gas clouds collided, triggering fireworks of star birth. Over time, these violent encounters sculpted galaxies into the diverse shapes we recognize today. Some grew into massive ellipticals puffed up by repeated collisions. Others, like our Milky Way, avoided catastrophic mergers and settled into delicate spiral arms. The legacy of proto-galaxies is written across the night sky. Every galaxy's size, shape, and even its starry population can be traced back to those chaotic early years. Without them, the universe would lack the rich tapestry of galaxies we see today. No majestic spirals, no glowing ellipticals, just a sea of disconnected stars. So the next time you spot Andromeda or the Sombrero Galaxy, remember, their stories began in the fury of those first, fragile proto-galaxies, where gravity turned chaos into cosmic architecture. At the heart of every galaxy's story lies an invisible architect, dark matter. Picture the universe's grandest structures, from swirling spirals to colossal clusters, all held together by something we can't even see. That's the paradox of dark matter. It doesn't emit, absorb, or reflect light, yet its gravitational grip shapes everything we observe. Without it, galaxies would fly apart like spinning tops, losing their balance, their stars scattering into the void. So how does this ghostly substance build galaxies? Imagine dark matter as the framework of an invisible skyscraper. In the early universe, it formed vast, web-like structures called halos, dense knots where gravity concentrated gas and dust. These halos acted like cosmic blueprints, guiding ordinary matter into the patterns we now recognize as galaxies. Computer simulations show this process in stunning detail. Dark matter's tendrils stretching across billions of light years, with galaxies blooming like dewdrops along a spider's web. But here's what's truly mind-bending: dark matter doesn't just hold galaxies together, it dictates their fate. The size and shape of a galaxy's dark matter halo determine whether it becomes a tightly wound spiral or a puffed-up elliptical. Even our Milky Way moves through space anchored to a halo weighing 1 trillion times more than our Sun. And yet, despite its overwhelming influence, dark matter remains elusive. Scientists have spent decades chasing it with underground detectors, particle colliders, and space telescopes, but it continues to defy direct observation. The mystery deepens when you consider what dark matter isn't. It's not black holes, it's not clouds of ordinary gas. It's something entirely foreign, a particle unlike anything in the standard model of physics. Some theories suggest it's a cosmic relic from the Big Bang, frozen in time. Others propose hidden dimensions or parallel universes. What we do know is this: the universe is far stranger than we imagined, with dark matter weaving an unseen tapestry that binds galaxies together. Every time astronomers measure the rotation of a distant galaxy or map the bending of light around a cluster, they're reading the fingerprints dark matter left behind. It's a reminder that the cosmos is full of secrets, and that the most powerful forces in the universe might be the ones we can't even see. So the next time you hear about a galaxy's dazzling stars or vibrant nebulae, remember, they're just the visible embroidery on a fabric woven from darkness. Deep in the hearts of those early galaxies, something monstrous was stirring. Supermassive black holes lurking like cosmic spiders at the center of invisible webs. These weren't just any black holes, they were titans weighing millions or even billions of times more than our sun, and their appetite was insatiable. Picture a whirlpool in space, sucking in gas, dust, even entire stars, growing larger with every meal. But here's the twist, these black holes didn't just sit there quietly feasting. They became the ultimate puppet masters, shaping the galaxies around them in ways we're only beginning to understand. How did these giants form so quickly in the young universe? One theory suggests they grew from the remnants of those first massive stars collapsing into black holes that then merged, gorged on gas, and ballooned in size. Others think they might have sprung directly from dense clumps of dark matter, bypassing the star stage entirely. Whatever their origin, their impact was immediate. As they fed, their gravity whipped surrounding gas into frenzied orbits, heating it to millions of degrees until it glowed brighter than all the stars in the galaxy combined. This is how quasars, the universe's first lighthouses, were born. Quasars are among the most dazzling objects in the cosmos. Imagine a single object outshining 1,000 Milky Ways, its light traveling billions of years to reach us. But that brilliance came at a cost. The energy pouring from these active black holes acted like a cosmic blowtorch, either igniting star formation in surrounding gas clouds or blasting them away entirely, starving the galaxy of future stars. It's a galactic tug of war. Feed the black hole and it might stifle the galaxy's growth, starve it, and the galaxy flourishes. This delicate dance between creation and destruction is written into the fabric of every galaxy we see today. And the wildest part, these ancient black holes didn't disappear. They're still here, lurking in galactic centers, including our own Milky Way. Sagittarius, a star, the supermassive black hole at our galaxy's heart, is a quiet giant now, but billions of years ago, it might have been a quasar shaping the very spiral arms we call home. That's the enduring legacy of these cosmic monsters. They're not just relics of the past, but active players in the universe's ongoing story. Every time astronomers peer into the heart of a distant galaxy, they're uncovering clues about how black holes and galaxies grew up together, locked in a gravitational embrace that's lasted since the dawn of time. Galaxies don't drift through space untouched. They crash, merge, and reshape each other in spectacular cosmic pileups. Think of it like a celestial demolition derby, where the collisions aren't endings but rebirths. When two galaxies collide, their stars rarely smash together. Space is too vast for that. Instead, their gravitational forces twist and stretch them like taffy, flinging stars into new orbits and compressing gas clouds until they ignite with newborn stars. These mergers are some of the most creative destruction the universe has to offer. Take the Milky Way. Right now, we're on a collision course with our neighbor, the Andromeda galaxy. In about 4 billion years, the two will meet in a slow-motion dance that'll last millions of years. Stars will be tossed into wild new trajectories, and the combined gravity might fling our solar system out into the galactic suburbs. But here's the twist. Instead of destruction, this chaos will birth something new, a giant elliptical galaxy nicknamed Andromeda. It's a reminder that in the cosmos, endings are just beginnings in disguise. But why do some galaxies grow while others fade? It all comes down to the merger's scale. When a large galaxy swallows a smaller one, it's like a cosmic snack. The bigger galaxy gains mass and fresh gas to fuel new stars. But when equals collide, the result is explosive. The antennae galaxies, two spirals caught mid-merger, are a perfect example. Their tangled arms sparkle with the pink glow of newborn stars, each one ignited by the shockwaves of colliding gas. Yet, over time, their delicate spirals will vanish, leaving behind a bloated elliptical galaxy, a relic of their violent embrace. These mergers aren't just ancient history. Telescopes catch them happening right now, like NGC 7742, a galaxy twisted into a ring by a smaller intruder. Even our own galactic backyard holds evidence. Streams of stars orbiting the Milky Way, the shredded remains of dwarf galaxies consumed long ago. Every merger leaves fingerprints, and astronomers piece together these clues like detectives solving a billion-year-old crime. What's truly astonishing is how mergers shape the universe's structure. Without them, galaxies would stay small and isolated, but gravity's relentless pull ensures they grow, cluster, and evolve. Some become titans, like the galaxy at the heart of the Virgo cluster, which has feasted on hundreds of others. Others, like our Milky Way, are still growing, their stories still being written. So the next time you see a galaxy's graceful spiral or a messy elliptical, remember, you're looking at a survivor of cosmic collisions, a testament to the universe's endless cycle of destruction and rebirth. Imagine the universe waking up from a deep sleep. For millions of years, it had been cloaked in a dense fog of hydrogen gas, a cosmic twilight where light couldn't travel far before being swallowed by the gloom. Then something extraordinary happened. The first stars and quasars flickered to life, their intense ultraviolet radiation piercing through that primordial haze like sunlight burning off morning mist. This was the epoch of re-ionization, a cosmic dawn that transformed the universe from opaque to transparent, forever changing how light could travel through space. The process didn't happen overnight. Picture a vast cosmic jigsaw puzzle where bubbles of ionized gas slowly expanded around early galaxies and quasars, eventually overlapping to clear the fog entirely. Ultraviolet photons packed with enough energy to strip electrons from hydrogen atoms acted like tiny demolition crews, breaking apart the neutral gas that had ruled the cosmos since the Big Bang. Over hundreds of millions of years, these bubbles grew, merging into a fully ionized universe where light could finally travel freely. How do we know this happened? The evidence is written in the light of the most distant quasars. When astronomers study their spectra, they find something peculiar, a forest of absorption lines caused by neutral hydrogen gas. The farther back they look, the thicker this forest becomes until, beyond a certain point, the light vanishes entirely. That cutoff marks the end of the Dark Ages, the moment when re-ionization completed its work. Telescopes like Hubble and the James Webb Space Telescope are now peering into this era, capturing galaxies caught in the act of clearing their surroundings, their young stars blazing trails through the cosmic fog. But re-ionization wasn't just about clearing the skies, it shaped the destiny of galaxies themselves. The same UV radiation that ionized the gas also heated it, making it harder for future galaxies to pull in fresh material. This put a brake on star formation, favoring larger galaxies that could hold onto their gas while smaller ones struggled. The universe became more selective, rewarding the strong and leaving the weak behind. Without re-ionization, the night sky would look utterly different. Distant galaxies would remain invisible, their light blocked by that ancient hydrogen fog. The cosmic web, the grand structure of galaxies we see today, might never have formed so clearly. It's a reminder that the universe's greatest transformations often hinge on the smallest details, like the relentless work of photons too tiny to see, yet powerful enough to illuminate the cosmos for eternity. So when you gaze at a starry sky, you're not just seeing points of light, you're witnessing the aftermath of a revolution, the moment the universe threw off its shroud and stepped into the light. Among the chaos of early galactic collisions and mergers, a quieter revolution was unfolding, one that gave birth to the universe's most iconic structures, spiral galaxies. Picture a vast, rotating disk of gas and stars, shimmering with delicate arms that spiral outward like the patterns of a cosmic whirlpool. These aren't static sculptures but dynamic, ever-changing masterpieces where gravity and motion conspire to create some of the most fertile grounds for star formation in the cosmos. So how do these spiral arms form? The secret lies in something called density waves. Imagine a traffic jam on a highway. Cars slow down as they enter the congestion, bunching up before speeding away again. In a spiral galaxy, stars and gas clouds behave similarly. As they orbit the galactic center, they encounter regions where gravity has compressed the material, creating waves of higher density. These waves don't move with the stars. Instead, they ripple through the disk like sound waves through air, triggering bursts of star formation as gas clouds collide and compress within them. That's why spiral arms often glow with the blue light of young, hot stars. They're the universe's most dazzling construction zones. But there's a puzzle here. If stars are constantly orbiting, why don't the arms wind up and vanish over time? This is where dark matter steps in again. The invisible halo surrounding a spiral galaxy acts like an anchor, stabilizing the disk and preventing the arms from dissolving. Even more telling are the galaxy's rotation curves, the way stars and gas move at different distances from the center. Instead of slowing down as you move outward, as Newton's laws would predict, the speeds remain high, a clear sign that unseen mass, dark matter, is holding everything together. Our own Milky Way is a classic example. Its elegant arms, like the Orion spur where our solar system resides, are studded with stellar nurseries like the Orion Nebula. But spiral galaxies aren't just pretty faces, they're galactic powerhouses. Their orderly rotation and abundant gas supply make them prolific star factories, constantly renewing their stellar populations. Compare that to elliptical galaxies, which are often red and dead, their gas long since used up or stripped away. Spirals, by contrast, are vibrant and alive, their arms brimming with the raw materials for new generations of stars. Yet even these majestic structures aren't permanent. Over billions of years, spiral galaxies can lose their delicate arms through collisions or by exhausting their gas reserves. Some may transform into ellipticals, their stars scattering into a shapeless haze. Others, like the Milky Way, might merge with neighbors, their spirals dissolving into something new. But for now, they dominate our night sky, their swirling arms a testament to the delicate balance of gravity, motion, and hidden forces that shape the universe. Every time you spot the faint band of the Milky Way overhead, you're glimpsing one of nature's most exquisite designs, a spiral galaxy in mid-creation, still writing its story across the cosmos. While spiral galaxies dazzle with their delicate arms and star-forming brilliance, their elliptical cousins tell a different story, one of cosmic upheaval and quiet endurance. Picture a galaxy shaped like a glowing football, its stars swirling in random orbits with no discernible disk or spiral structure. These are elliptical galaxies, the universe's silent giants, and their smooth, featureless appearance hides a turbulent past. Unlike spirals, which thrive on orderly rotation, ellipticals are the aftermath of galactic chaos, their stars jostling like a crowd after a concert, their gas long since stripped away or used up. What created these enigmatic giants? The answer lies in some of the most violent events in the cosmos, galactic collisions. When two spiral galaxies of similar size collide, their delicate disks are shredded by gravitational forces. Stars are flung into chaotic orbits while their gas clouds crash together, triggering one final burst of star formation before the fuel is exhausted. Over time, the merged galaxy settles into a smooth, rounded shape, no spirals, no disk, just a vast swarm of aging stars. The result is a celestial retirement home where stellar birth rates are near zero, and the population is dominated by ancient red giants and white dwarfs. But don't let their quiet demeanor fool you. Ellipticals are often the most massive galaxies in the universe, reigning at the centers of galaxy clusters like monarchs on thrones. Take Messier 87, the supergiant elliptical anchoring the Virgo cluster. Its sheer size is staggering, a trillion stars held together by gravity, with a supermassive black hole at its heart so enormous it could swallow our solar system without a hiccup. These galaxies aren't just products of mergers, they're proof of the universe's relentless drive to consolidate, to build ever larger structures through sheer gravitational might. Yet ellipticals aren't entirely lifeless. Some, like NGC 1277, hide surprising secrets, vast reservoirs of hot gas glowing in X-rays, or faint shells of stars left behind by ancient mergers. These features are like cosmic fingerprints, clues to the violent events that shaped them. Even their star populations tell a story. The redder the galaxy, the older its stars, with little of the blue light from young, hot stars that illuminate spirals. It's a stark reminder that galaxies, like living things, change over time, their appearances reflecting their histories. What's truly fascinating is how ellipticals dominate the social hubs of the universe. While spirals prefer solitude or small groups, ellipticals crowd into galaxy clusters where frequent interactions have long since erased their spiral structure. This dichotomy, spirals as star-forming loners, ellipticals as retired giants in cosmic cities, shows just how deeply a galaxy's environment shapes its fate. So the next time you see an image of a smooth, golden ellipse in a telescope survey, remember, you're looking at the end result of a cosmic demolition derby, a galaxy that has lived through collisions and come out the other side. Its quiet glow is a testament to the universe's capacity for both violence and transformation, a reminder that even in the vastness of space, nothing stays the same forever. Not every galaxy fits neatly into the categories of spiral or elliptical. Some are cosmic misfits, rebels without a clear structure, swirling in chaotic splendor. These are irregular galaxies, the universe's rule breakers, where stars and gas clouds clump together in seemingly random patterns, defying the elegant order of their more symmetrical cousins. Picture an artist's palette flung onto a canvas, vibrant and untamed. That's the essence of an irregular galaxy. What makes these galaxies so delightfully disordered? Often, it's the gravitational meddling of larger neighbors. Take the Large Magellanic Cloud, our Milky Way's most famous satellite galaxy. Though it shows hints of a loose spiral structure, its shape is warped and lopsided, stretched by the Milky Way's relentless pull. Other irregulars, like the Wolf-Lundmark-Melot galaxy, are lone wanderers, their asymmetry born from internal drama-frenzied bursts of star formation that churn up their gas clouds like a cosmic blender. But don't mistake their chaos for insignificance. Irregular galaxies are cosmic laboratories, offering a glimpse into the raw, unfiltered processes of galactic evolution. Without the stabilizing influence of a dense dark matter halo or a central bulge, their gas remains loose and turbulent, making them hotbeds for starburst activity. In galaxies like IC10, stars ignite at rates dozens of times faster than in the Milky Way, their brilliant blue clusters lighting up the darkness like fireworks. These starbursts don't just shape the galaxy, they flood the cosmos with heavy elements, seeding future generations of stars and planets. Yet irregular galaxies are also fleeting. Their lack of structure makes them vulnerable. Some, like the Sagittarius dwarf Irregular, are slowly being torn apart by the gravity of larger galaxies, their stars strewn across the cosmic void. Others may eventually settle into more orderly shapes if left undisturbed, their gas coalescing into disks or spheroids over billions of years. What's most captivating about these galactic rebels is what they teach us. In a universe that often seems governed by strict rules, irregular galaxies remind us that chaos has its place. They're the cosmic equivalent of wildflowers in a meticulously trimmed garden, unexpected, beautiful, and proof that nature's creativity knows no bounds. So the next time you see an image of a shapeless, glowing haze in deep space, look closer. You might be witnessing a galaxy that refuses to conform, a reminder that even in the cosmos, there's room for the untamed. Deep within every galaxy, hidden forces are at work, forces so powerful they can fling entire oceans of gas into the void, shaping the galaxy's destiny in the process. These are galactic winds, cosmic hurricanes fueled by the most violent events in the universe, supernova explosions, and the ravenous appetites of supermassive black holes. Picture a star dying in a cataclysmic blast, its shockwaves rippling through surrounding gas clouds at millions of miles per hour. Or envision a black hole's fury, its intense radiation and magnetic fields launching jets of material into intergalactic space. These aren't just spectacular light shows, they're the galaxy's own self-regulating mechanisms, a delicate balancing act between creation and destruction. Take the Starburst Galaxy Messier 82, a tempest of star formation where supernova erupt like clockwork. Each explosion acts like a cosmic bellows, driving gas outward in vast, shimmering waves. Without these winds, the galaxy would burn through its fuel in a frenzy of star birth, leaving it barren and lifeless in just a few 100 million years. But the winds do more than just slow things down, they enrich the cosmos. As they surge outward, they carry heavy elements forged in stellar cores, scattering them across intergalactic space like seeds in the wind. Future generations of stars and planets will form from this recycled material, each one carrying traces of those ancient explosions. Then there's the role of supermassive black holes, which take feedback to a whole new level. When a black hole feeds, it doesn't just swallow matter quietly. It spews out colossal jets and radiation, heating surrounding gas to millions of degrees. In galaxies like Cygnus A, these jets stretch for hundreds of thousands of light years, carving bubbles in the intergalactic medium. The energy released is staggering, enough to shut down star formation across an entire galaxy. It's a cosmic paradox. The same force that builds galaxies with its gravity can also stunt their growth with its fury. This feedback loop is why galaxies evolve at such different rates. Some, like our Milky Way, maintain a steady pace of star formation, thanks to gentle winds that prevent gas from collapsing too quickly. Others, like the massive ellipticals at the centers of galaxy clusters, have had their gas reservoirs blasted away entirely, leaving them red and dead, with no new stars for billions of years. Even dwarf galaxies feel the effects. Their weaker gravity makes them especially vulnerable to having their gas stripped away by winds from neighboring giants. The echoes of these processes are everywhere. When astronomers look at the faint glow of gas between galaxies, they're seeing the legacy of countless supernova and black hole outbursts, a diffuse ocean of material that might one day fall back into galaxies, fueling new cycles of birth and destruction. It's a reminder that galaxies aren't isolated islands, they're dynamic ecosystems, breathing in and out as they dance with the cosmos. Every star, every planet, every living thing owes its existence to this grand interplay between chaos and balance, where even the most violent events serve a purpose in the universe's unfolding story. Galaxies aren't immortal, they age, change, and sometimes they simply stop creating new stars. This cosmic retirement, known as quenching, turns vibrant, star-forming galaxies into what astronomers call red and dead systems, smooth, reddish ellipticals where the lights of young blue stars have long since faded. But why does this happen? The answer lies in a delicate tug of war between a galaxy's ability to hold onto its gas and the forces determined to take it away. Take gas depletion first. Galaxies need a steady supply of cold gas to form stars, but in dense environments like galaxy clusters, that fuel can vanish fast. Picture a galaxy moving through a cluster's hot intergalactic medium. It's like a car driving through a sandstorm. The pressure strips away its gas, leaving it starved and unable to create new stars. This process, called RAM pressure stripping, is brutally efficient. The galaxy's star-forming factories shut down one by one, leaving behind only aging red giants and the faint glow of white dwarfs. Then there's feedback, both from stars and supermassive black holes. When a galaxy forms too many stars too quickly, the resulting supernova explosions can blast gas right out of the galaxy, like a hurricane clearing a forest. But the real game changer is the central black hole. As it feeds, it releases torrents of energy, heating surrounding gas to millions of degrees until it's too hot to collapse into new stars. In extreme cases, these outbursts can blow away an entire galaxy's gas reserves in a single cosmic tantrum. Environment plays a role, too. Galaxies in crowded clusters are more likely to be quenched than those in quieter cosmic suburbs. Gravitational interactions with neighbors can disrupt their gas supplies, while the intense heat of the cluster's central regions makes it nearly impossible for gas to cool and condense. It's like trying to build a snowman in a sauna. Conditions just aren't right. But here's the twist: quenching isn't always permanent. Some galaxies, like NGC 4522, a rare, rejuvenated elliptical, show signs of late-life star formation, suggesting they've somehow scavenged or recycled gas to spark a second act. Even our Milky Way isn't immune to quenching's grip. Right now, it's still a star-forming powerhouse, but in a few billion years, as its gas runs low and its black hole grows more active, it too may fade into the red and dead population. Studying these quenched galaxies is like reading the universe's obituaries. Each one tells us how galaxies live, age, and ultimately die. They remind us that even in the cosmos, nothing lasts forever, and that the most majestic structures are subject to the same unyielding laws of time and physics. The next time you see a smooth, golden-hued elliptical in a telescope image, remember, you're not just looking at a galaxy, you're looking at a cosmic fossil, a relic of a once-thriving system that has reached the end of its stellar story. Galaxies aren't always the polite neighbors we imagine. Sometimes they're outright predators. In the cosmic food chain, larger galaxies grow by devouring smaller ones, a process astronomers call galactic cannibalism. Think of it like a cosmic version of Pac-Man, where massive galaxies gobble up their dwarf counterparts, absorbing their stars, gas, and even dark matter. This isn't just a rare event, it's a fundamental part of how galaxies evolve, and our own Milky Way is no exception. Over its 13.6 billion-year lifetime, it's swallowed at least a dozen smaller galaxies, each merger leaving behind ghostly trails of stars as evidence. Take the Sagittarius dwarf spheroidal galaxy, one of the Milky Way's most recent meals. Once an independent galaxy, it's now stretched into a long, looping stream of stars orbiting our galactic core, a celestial ribbon unraveled by gravity's relentless pull. Then there's the Gaia sausage, the remains of a dwarf galaxy that collided with the Milky Way around 10 billion years ago. Its stars didn't just blend in, they were hurled into wild, radial orbits, forever marking the violence of that ancient merger. These stellar streams are like cosmic breadcrumbs, helping astronomers piece together our galaxy's violent history. But galactic cannibalism isn't just about growth, it's about enrichment. Smaller galaxies often carry pockets of pristine gas, untouched by the heavy elements forged in larger galaxies. When they're absorbed, that gas floods into the larger galaxy, fueling new waves of star formation. It's like adding fresh ingredients to a stew, giving the galaxy a richer, more complex chemical makeup. Some of the Milky Way's oldest stars, like those in the halo, are thought to be refugees from these devoured dwarfs, their compositions telling the story of their origins. The process isn't always gentle. When a dwarf galaxy falls into a larger one, tidal forces stretch it into streams, while its dark matter halo, if it had one, slowly merges with the host galaxy's own invisible scaffold. Over time, the smaller galaxy's identity is erased, its stars scattered like confetti in a galactic wind. Yet, without these mergers, galaxies like ours would look very different. They'd be smaller, poorer in metals, and far less dynamic. Even now, the Milky Way is eyeing its next meal. The Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, is on a collision course. In about 2.5 billion years, it's expected to plunge into our galaxy, triggering another burst of star formation and reshaping our cosmic home once again. Galactic cannibalism isn't just a relic of the past, it's an ongoing saga, a reminder that even the grandest structures in the universe are built on a foundation of countless smaller conquests. Every giant galaxy has its entourage, tiny cosmic followers known as satellite galaxies. These dwarf galaxies, some containing just a few million stars, orbit their larger counterparts like moths circling a flame. But don't let their size fool you. These satellites are more than just decorative. They're gold mines of information, helping astronomers unravel two of the universe's biggest mysteries: dark matter and galaxy formation. Take the Milky Way satellite system. Over 50 dwarf galaxies orbit our home galaxy, from the Large Magellanic Cloud, a star-forming powerhouse visible to the naked eye, to ultra-faint dwarfs like Draco and Ursa Minor, which are so dim they were only discovered in the past few decades. The way these satellites are arranged isn't random. Their orbits trace the contours of our galaxy's dark matter halo, revealing its shape and density like iron filings mapping a magnetic field. Without dark matter's gravitational grip, these tiny galaxies would have long since drifted away or been torn apart. Some, like the Sagittarius dwarf, are already paying the price for getting too close. Stretched into a gossamer stream of stars by the Milky Way's tidal forces, it's a living example of galactic digestion in action. But even as it dissolves, it leaves behind clues. The stars it sheds form delicate arcs around our galaxy, marking the path of its orbit like breadcrumbs. By studying these trails, astronomers can reconstruct the Milky Way's gravitational field in 3 dimensions, a cosmic autopsy that tells us not just where the dark matter is, but how it's distributed. These satellites are also time capsules from the early universe. Many, like Segway 1, are ancient. Their stars formed over 13 billion years ago, before heavy elements were common. They're relics of a time when galaxies were just beginning to assemble, pristine examples of the building blocks that merged to create giants like the Milky Way. Their simple structures and chemical makeup offer a snapshot of galactic infancy, a contrast to the complex spirals and ellipticals we see today. Yet there's a puzzle. According to simulations, our galaxy's dark matter halo should host hundreds of satellites, not dozens. This missing satellites problem has kept astronomers busy for years. Some suggest that many dwarfs are too faint to detect, their stars scattered by eons of tidal forces. Others propose that dark matter behaves differently on small scales, preventing some satellites from forming stars at all. Either way, these elusive galaxies are pushing our understanding of cosmology to its limits. From mapping invisible matter to preserving the universe's oldest stars, satellite galaxies are proof that sometimes the smallest objects hold the biggest secrets. They remind us that galaxies don't evolve in isolation, they're part of a dynamic, interconnected system, where even the tiniest members have a story to tell. Some galaxies don't just form stars, they explode with them, igniting in brilliant, short-lived frenzies that outshine entire galaxies. These are starburst galaxies, the cosmic equivalent of fireworks, where star formation isn't a steady process but a dazzling, all-consuming blaze. Picture a galaxy where new stars ignite hundreds or even thousands of times faster than in our Milky Way, their collective light so intense it can be seen across the universe. But what triggers these spectacular outbursts? The answer lies in chaos collisions, mergers, or sudden floods of gas that shake a galaxy to its core. Take the antennae galaxies, two spirals locked in a slow-motion collision. As their gas clouds slam together, shockwaves ripple through them, compressing the gas into dense knots where stars ignite like matches struck in quick succession. The result, a galaxy ablaze with newborn stars, their blue-white light overpowering the older, yellower population. Or look at Messier 82, a starburst galaxy so active its core resembles a supernova factory, with explosions so frequent they drive colossal winds of gas outward at millions of miles per hour. These aren't just pretty light shows, they're galactic turning points, reshaping a galaxy's structure and future in mere millions of years. Yet starbursts are fleeting by cosmic standards. Like a wildfire burning through dry brush, they consume their fuel with reckless abandon, exhausting their gas reserves in a fraction of the time it takes most galaxies to form even a modest number of stars. Once the gas is gone, the starburst fades, leaving behind a galaxy that's older, redder, and quieter, a retired superstar with only the echoes of its glory days. What makes starbursts so crucial to galactic evolution is their sheer efficiency. In these fiery crucibles, heavy elements like carbon, oxygen, and iron are forged at breakneck speeds, then scattered into space by supernova and stellar winds. This enriched material becomes the raw ingredient for future stars, planets, and even life. Without starbursts, the universe might lack the chemical diversity needed to build complex worlds. But starbursts aren't just about creation, they're also about destruction. The same processes that birth stars can also tear galaxies apart. Radiation from massive young stars heats and ionizes surrounding gas, while supernova blast it away entirely. In extreme cases like the nearby Hennies 210, starburst activity can even trigger the growth of supermassive black holes, linking these fiery episodes to the broader story of galactic evolution. These cosmic fireworks remind us that the universe is anything but static. In starburst galaxies, we see nature's capacity for both beauty and violence, a reminder that even the grandest structures are shaped by moments of breathtaking intensity. They're fleeting, yes, but in their brief, brilliant lives, they light the way for everything that follows. At the heart of some galaxies, something extraordinary is happening, a cosmic engine so powerful it can outshine every star in its host galaxy combined. These are active galactic nuclei, or AN, the universe's ultimate power plants, fueled by supermassive black holes feeding on surrounding gas and dust. But this isn't just a quiet feast, it's a spectacle of physics pushed to extremes, where matter doesn't just vanish into darkness. Instead, it's heated to millions of degrees, accelerated to near light speeds, and blasted into space as jets of energy that can stretch for thousands of light years. Quasars are the most dazzling members of this family. Imagine an object no larger than our solar system, yet brighter than 1 trillion suns, so luminous it can be seen from the edge of the observable universe. These are the cores of young galaxies, their black holes gorging on gas during the cosmos's most ravenous era. What makes quasars so fascinating isn't just their brilliance, but their role as cosmic lighthouses. Their light, traveling for billions of years, carries clues about the early universe's structure, revealing the distribution of gas and galaxies along its path. But AGN aren't just celestial curiosities, they're galactic sculptors. The energy they release does more than light up the cosmos. It shapes the very galaxies they inhabit. Jets streaming from the black hole can carve vast bubbles in surrounding gas, while intense radiation heats interstellar material, preventing it from cooling and forming new stars. This feedback mechanism is a cosmic balancing act. Too much activity, and the galaxy is starved of star-forming fuel. Too little, and it might overproduce stars, exhausting its resources too quickly. Some of the most dramatic examples lie in galaxy clusters, where AGN act like cosmic thermostats. In systems like the Perseus cluster, jets from the central galaxy's black hole pump energy into the surrounding hot gas, preventing it from cooling and funneling onto the galaxy itself. Without this heating, galaxy clusters would form stars at runaway rates, altering the universe's large-scale structure. Yet AGN are also ephemeral. A black hole's feast can't last forever. Once nearby gas is depleted, the brilliance fades, leaving behind a quieter core like the one in our Milky Way. But the legacy remains, the heavy elements forged in these maelstroms, the shockwaves that stirred galactic gas, even the way galaxies are distributed in space, all bear the fingerprints of AGN activity. They remind us that even the darkest objects in the universe can light the way, shaping galaxies across cosmic time. Gravity doesn't just shape galaxies, it builds metropolises. Imagine a city where the skyscrapers are galaxies, the streets are threaded with superheated gas, and the invisible infrastructure is woven from dark matter. This is a galaxy cluster, the universe's ultimate gathering place, where thousands of galaxies orbit a common center, bound together in a gravitational dance that's lasted billions of years. These clusters aren't just random crowds, they're cosmic ecosystems, teeming with interactions that reveal how galaxies grow, collide, and evolve in the busiest corners of the universe. Take the Virgo cluster, our local galactic cityscape. Located about 54 million light-years away, it's home to over 1,000 galaxies, all swirling around a central giant, Messier 87, a supermassive elliptical galaxy with a jet-spewing black hole at its core. But the real surprise isn't the galaxies, it's what fills the space between them. The cluster is suffused with a thin, scorching gas, heated to millions of degrees and glowing in X-rays. This gas isn't just leftover debris, it's a dynamic component of the cluster, a reservoir of material that can fuel new stars or be siphoned away by gravitational tides. Then there's the dark matter, which makes up nearly 90% of the cluster's mass. Like invisible scaffolding, it molds the cluster's shape, dictating how galaxies move and where gas collects. We can't see it directly, but its presence is undeniable. When astronomers measure the speeds of galaxies within clusters, they find they're moving too fast to be held together by visible matter alone. Without dark matter's grip, these galactic cities would fly apart, their members scattering into the void. What's truly astonishing is how clusters evolve. They grow by swallowing smaller galaxy groups, a process that's anything but gentle. When a group falls into a cluster, its galaxies are stripped of gas by the pressure of the hot intracluster medium, a phenomenon called Ram pressure stripping. The result, galaxies that were once vibrant spirals become red and dead ellipticals, their star-forming fuel ripped away. Meanwhile, the cluster's central galaxy, often a behemoth like Messier 87, grows even larger, feasting on its neighbors in a relentless cycle of galactic cannibalism. Clusters also act as cosmic lenses. Their immense gravity bends light from more distant objects, magnifying them like a telescope. This effect, called gravitational lensing, lets astronomers peer even deeper into the universe, spotting galaxies that would otherwise be too faint to see. It's as if the cluster itself becomes a window, revealing the universe's most distant secrets. Yet for all their grandeur, galaxy clusters are also time capsules. Their galaxies tell the story of cosmic evolution, from the frenzied star formation of the early universe to the quieter, more settled era we see today. And the hot gas between them, it's laced with heavy elements forged in supernova and black hole outbursts, a testament to the cycles of creation and destruction that have shaped the cosmos. So the next time you look at a deep field image of a galaxy cluster, remember, you're not just seeing a snapshot of space, you're witnessing a dynamic, ever-changing community where galaxies live, interact, and transform under the watchful eye of gravity. These clusters are more than the sum of their parts. They're the universe's way of building something greater, one galaxy at a time. The universe isn't just a random sprinkling of galaxies, it's a meticulously woven tapestry, threaded together by colossal filaments of dark matter and gas that stretch across billions of light years. These cosmic filaments are the backbone of the universe, the invisible scaffolding upon which everything is built. Picture them like the roots of a gargantuan tree, branching out in every direction, connecting galaxy clusters at their intersections and leaving vast, empty voids between them. This is the cosmic web, the largest structure in existence, and it holds the key to understanding how galaxies form, grow, and move through space. At the heart of this web lies dark matter, the unseen architect. Though invisible, its gravitational pull sculpts the filaments, drawing ordinary matter, hydrogen and helium gas into these meandering rivers. Over time, gravity works its magic, pulling gas along the filaments like water flowing through a network of pipes. Where these streams intersect, galaxies and clusters form, fed by the constant supply of raw material. It's a cosmic delivery system, ensuring that the universe's largest structures never run out of fuel. The scale of these filaments is almost incomprehensible. Some span hundreds of millions of light years, threading through the void like bridges between islands of galaxies. The Sloan Great Wall, one of the biggest known structures, is a filament so vast it would take light nearly 1.5 billion years to travel from one end to the other. And yet, despite their enormity, these filaments are surprisingly delicate. The gas within them is so diffuse that, if you stood inside one, you wouldn't even know it was there, just a few atoms per cubic meter, far emptier than the best vacuum we can create on Earth. What's truly astonishing is how these filaments shape galactic destiny. Galaxies born along these cosmic highways grow faster and larger, fed by the steady stream of gas. Those stranded in the voids, cut off from the web, often remain small and stunted, their star formation stifled by isolation. Even the motion of galaxies is dictated by the filaments, as they slide along these dark matter thoroughfares like cars on a freeway, pulled toward the densest clusters where gravity's grip is strongest. But the cosmic web isn't static. It evolves over time, with filaments growing thicker as gravity pulls more matter into them, while the voids between them stretch ever larger. Computer simulations like the famous Illustris project show this process in stunning detail, filaments forming, merging, and reshaping the universe in an endless dance. And as telescopes like the James Webb Space Telescope peer deeper into the cosmos, they're capturing glimpses of this web in its infancy, when the universe was just a fraction of its current age. The cosmic web is more than just a curiosity, it's a window into the universe's deepest mysteries. By studying its structure, astronomers can trace the history of dark matter, map the flow of gas across cosmic time, and even predict where new galaxies will form. It's a reminder that, on the grandest scales, the universe is anything but random. Every galaxy, every cluster, every swirling spiral is part of a vast, interconnected network, bound together by threads of darkness and light. Between the great cosmic filaments, where galaxies cluster like cities along invisible highways, lie the universe's most desolate regions, the voids. These are not just empty patches but staggering abysses of nothingness, some stretching over 300 million light-years across. To put that in perspective, if our Milky Way were a grain of sand, crossing a void would be like traversing an ocean wider than the Earth. Yet despite their emptiness, these voids are anything but insignificant. They are the counterbalance to the cosmic web, the silent expanses that define the universe's structure just as much as the glittering galaxies do. What makes voids so fascinating is how they shape the motion of everything around them. Picture a rolling landscape where galaxies slide downhill toward the densest clusters, pulled by gravity's relentless tug. But voids are the valley's regions of such low density that they exert a kind of negative gravity, repelling matter rather than attracting it. This means galaxies near voids don't just sit still, they're pushed away, accelerated by the absence of mass as much as by the presence of it. It's a cosmic game of push and pull, where emptiness is just as influential as matter. The Boötes Void is one of the most famous and eerie examples. Discovered in the 1980s, it's a spherical chasm roughly 330 million light-years wide, containing only a handful of galaxies where there should be thousands. Astronomers call it the Great Nothing, a place so empty that if you were at its center, the night sky would appear almost starless, a vast black canvas with only the faintest pinpricks of light. Yet even here, the void isn't completely barren. The few galaxies that do exist are often oddballs, isolated, gas-poor, and strangely shaped, as if the void itself has starved them of companionship and resources. Voids also play a crucial role in the universe's expansion. Because there's so little matter to slow it down, space within voids stretches faster than in denser regions. This uneven expansion creates subtle ripples in the cosmic web, tugging filaments and clusters in ways that astronomers are only beginning to map. In a sense, voids are the universe's accelerators, regions where dark energy's influence is most pronounced, silently driving galaxies apart. Yet for all their emptiness, voids are not static. Over billions of years, they grow larger as filaments siphon away the last traces of gas and galaxies. Some may even merge, creating supervoids that span nearly a billion light-years. Others might eventually be refilled. If dark energy's push falters, gravity could one day draw matter back into these deserted regions, sparking new cycles of star formation in the most unlikely places. The existence of voids forces us to confront a humbling truth. The universe is not just a collection of galaxies, but a dynamic interplay between presence and absence. For every shining cluster, there's a corresponding void, a yin to the cosmic yang. They remind us that emptiness is not just a backdrop but an active player in the story of the cosmos, shaping its past, present, and future in ways we're only beginning to understand. So the next time you look up at the night sky, remember, what's not there is just as important as what is. The story of our Milky Way isn't just written in textbooks, it's etched across the night sky in ancient stars and strewn galactic debris. Like cosmic archaeologists, astronomers piece together our galaxy's past by studying its oldest inhabitants, globular clusters. These dense balls of stars, some over 13 billion years old, are time capsules from the Milky Way's infancy. Unlike younger stars that orbit in the galaxy's flat disk, these ancient clusters form a spherical halo around us, their random paths tracing the chaotic conditions of the early universe when our galaxy was just taking shape. One remarkable cluster, Messier 92, contains stars born when the universe was less than 1 billion years old. Their chemical makeup, almost pure hydrogen and helium with barely a trace of heavier elements, reveals they formed before supernova had enriched the cosmos with metals. These primordial stars are like living fossils, preserving the Milky Way's earliest days when it was little more than a collection of gas clouds and proto-galactic fragments. But our galaxy didn't grow in isolation. The Gaia spacecraft's stunning 3D maps have revealed ghostly stellar streams, ribbons of stars winding through the Milky Way's halo. These are the remains of smaller galaxies torn apart by our galaxy's gravity, their stars gradually assimilated into ours. The most dramatic example is the Gaia-Enceladus merger, a dwarf galaxy that collided with the Milky Way about 10 billion years ago. This cosmic crash injected our galaxy with fresh stars and gas, likely triggering a burst of star formation that helped build the thick disk we see today. Even now, the Milky Way is still growing. The Sagittarius dwarf spheroidal, one of our current satellite galaxies, is being slowly shredded by tidal forces, its stars painting streaks across our sky. And in about 4 billion years, the colossal Andromeda merger will fundamentally reshape our galactic home. Computer simulations show the two spirals tangling together, their stars flung into new orbits until they form a single, football-shaped elliptical galaxy, dramatic proof that galaxies aren't static islands but ever-changing systems. What makes the Milky Way special isn't just its history, but how typical it is. By studying our galaxy's growth through mergers and star formation cycles, astronomers recognize the same patterns in distant galaxies. We're witnessing universal processes up close. The same forces that built galaxies across the cosmos also built the spiral we call home. Every time we map a new stellar stream or date an ancient cluster, we're not just learning about the Milky Way. We're reading a chapter in the universe's grand story of galactic evolution. The Andromeda Galaxy isn't just another spiral in the night sky, it's the Milky Way's cosmic twin, a looking glass that lets us study our own home from the outside. At 2.5 million light-years away, Andromeda is the closest major galaxy to us, close enough that its shimmering disk is visible to the naked eye as a faint smudge in the autumn sky. But don't let its serene appearance fool you. This galactic sibling has lived a far more turbulent life than the Milky Way, bearing scars from ancient collisions that reveal just how chaotic galactic evolution can be. One of Andromeda's most striking features is its size, spanning 220,000 light-years, nearly double the Milky Way's width. It's the heavyweight of our local group. Its vast disk is littered with the remnants of past mergers, including a giant stellar halo that stretches far beyond its spiral arms. This halo is like a cosmic crime scene, strewn with stars ripped from smaller galaxies Andromeda has devoured over billions of years. The Gaia spacecraft recently uncovered evidence of one particularly violent feast, a dwarf galaxy named M32P, which Andromeda tore apart so thoroughly that only its dense core remains today, orbiting like a ghost of its former self. Andromeda's central black hole also tells a story of excess. Weighing in at 100 million solar masses, it's over 20 times more massive than Sagittarius, a star at the heart of the Milky Way. Surrounding it is a bizarre double nucleus, two dense clumps of stars orbiting each other like dancers, locked in a gravitational embrace. Astronomers believe this is the aftermath of a galactic merger, where a smaller galaxy's black hole spiraled into Andromeda's core, stirring up stars in its wake. Yet the most dramatic chapter in Andromeda's story is yet to come. Right now, it's hurtling toward the Milky Way at 250,000 miles per hour, pulled by the irresistible tug of gravity. In about 4 billion years, the two galaxies will meet in a slow-motion collision that will reshape them both. Computer simulations show their spiral arms tangling like celestial brushstrokes, stars flinging into new orbits as tidal forces warp their disks. Over millions of years, they'll merge into a single, football-shaped elliptical galaxy dubbed Andromeda by astronomers, a hybrid beast where the night sky would glow with the combined light of 1 trillion stars. What makes Andromeda such a priceless laboratory isn't just its fate, but its contrasts. While the Milky Way has grown through steady, smaller mergers, Andromeda's history is written in bold strokes, a testament to the diverse paths galaxies can take. By studying its scars, its structure, and even its doomed dance with our own galaxy, we're not just peering into the future, we're uncovering the universal forces that have shaped every shining spiral in the cosmos. Deep in the heart of our galaxy, ancient stars whisper secrets about the Milky Way's wild youth. These celestial elders, some nearly as old as the universe itself, carry chemical imprints in their light that reveal where and when they were born, like cosmic birth certificates written in spectral lines. This isn't just stargazing, it's galactic archaeology, where astronomers don't dig through dirt but sift through starlight, reconstructing our galaxy's history one element at a time. Take the metal-poor stars scattered through the Milky Way's halo. Their atmospheres contain barely a trace of elements heavier than hydrogen and helium, clear evidence they formed before generations of supernova enriched the cosmos with metals. Stars like HD 14283, nicknamed the Methuselah star, have such pristine compositions they must have been among the first to ignite in our galaxy's turbulent infancy. By measuring these chemical fossils, astronomers can trace how the Milky Way grew from a small clump of gas to the grand spiral we see today. But the real breakthrough came when scientists noticed distinct groups of stars sharing similar chemical signatures and orbits, like finding pottery shards from the same ancient civilization. These stellar families are the remnants of dwarf galaxies swallowed by the Milky Way long ago. One group, called the Sequoia event, consists of stars with unusual orbits and metal contents that suggest they came from a single dwarf galaxy devoured 9 billion years ago. Another, the Gaia Sausage, is the debris of a head-on collision that may have triggered our galaxy's last major burst of star formation. Modern telescopes have turned this cosmic detective work into precision science. The Gaia spacecraft maps billions of stars in 3 dimensions, tracking their motions to reconstruct past mergers. Spectrographs like those on the Very Large Telescope dissect starlight with such accuracy they can detect elements present in just 1 part per billion, equivalent to finding a single grain of salt in an Olympic-sized swimming pool. These tools reveal not just where stars are now, but where they came from, painting a vivid picture of galactic cannibalism spanning billions of years. What's emerging is a story of growth through violence. The Milky Way didn't form peacefully. It built itself by tearing apart smaller galaxies and absorbing their stars. Each merger left behind chemical breadcrumbs, extra neutron-rich elements from rapid supernova in dwarf galaxies, or distinct ratios of magnesium to iron that betray a star's birthplace. Even our Sun carries hints of this chaotic past, with trace elements that suggest it formed from gas enriched by multiple generations of stellar explosions. The most astonishing part, this isn't unique to our galaxy. When astronomers study Andromeda's halo, they find similar stellar streams and chemical patterns, proof that all large galaxies grow through the same relentless cycle of mergers and assimilation. Galactic archaeology doesn't just uncover our past, it reveals the universal recipe for building a galaxy, written in the elements that make up everything from distant stars to the iron in our blood. Every time we analyze the light of an ancient star, we're reading a page from the Milky Way's autobiography, one that's still being written with every new discovery. The cosmic story of galaxies isn't ending, it's entering a new chapter, one where the universe itself becomes the architect of change. Picture the night sky billions of years from now, transformed by forces both grand and gradual. The Milky Way and Andromeda will have long since merged, their spiral arms erased into a glowing elliptical blob, while smaller galaxies continue falling prey to larger ones in an endless cycle of galactic digestion. Star formation, once a vibrant spectacle, will slow to a trickle as galaxies exhaust their gas reserves, leaving behind aging stellar populations that glow redder and dimmer with each passing eon. The universe, once ablaze with youthful energy, will grow quieter, darker, and colder, a far cry from the fiery brilliance of its early years. Yet this isn't just a story of decline. Even as galaxies fade, they'll continue to evolve in unexpected ways. Supermassive black holes, now dormant in many galactic cores, may awaken for one final feast, consuming the last traces of gas and dust to unleash fleeting bursts of light. Isolated stars, flung into the voids during past collisions, might ignite sporadic novas in the darkness, like embers glowing in a dying fire. And while the era of massive spiral galaxies will pass, new structures could emerge: ultra-diffuse galaxies floating like ghosts in the expanding void, or dark matter halos merging silently in the absence of starlight. The universe's expansion adds another twist to this cosmic epilogue. As space stretches faster, distant galaxies will vanish beyond an invisible horizon, their light no longer able to reach us. The local group, our galactic neighborhood, will become an island in an ever-growing sea of emptiness, its member galaxies bound together by gravity but cut off from the rest of the cosmos. Future civilizations, if any exist, would gaze upon a sky nearly devoid of external galaxies, their universe reduced to a handful of aging stars and the remnants of long-dead giants. But before that distant twilight, there's still so much to uncover. Next-generation telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will probe deeper into galactic histories, uncovering faint stellar streams or hidden black holes that rewrite our understanding of cosmic evolution. Dark matter's secrets, the true nature of galactic feedback, even the possibility of undiscovered physics. All these mysteries linger, waiting for the right observer or instrument to reveal them. The future of galaxies isn't just a slow fade to black. It's a reminder that the universe is dynamic, unpredictable, and full of surprises even in its twilight years. Every collision, every fading star, every silent merger is part of a story that began with the Big Bang and will continue long after the last star winks out. The cosmos doesn't end, it transforms, and in that transformation lies its enduring fascination. Right now, as galaxies spin and collide, an invisible force is working against them, not gravity, but its opposite. Dark energy, the universe's most enigmatic ingredient, isn't just present. It's dominant, making up nearly 70% of the cosmos. Unlike gravity, which pulls matter together, dark energy pushes space itself apart, accelerating the expansion of the universe in every direction. Picture a loaf of raisin bread baking in an oven, except the dough is space and the raisins are galaxies. As the bread rises, the raisins don't move. The space between them stretches, carrying them farther apart. That's the universe under dark energy's influence, a cosmic tug of war where expansion wins every time. What makes dark energy so baffling isn't just its effect, but its timing. For the first 9 billion years after the Big Bang, gravity had the upper hand. Galaxies clustered, filaments thickened, and the cosmic web grew denser. Then, around 5 billion years ago, something flipped. Dark energy's repulsive force overcame gravity's pull, and the expansion began speeding up. Telescopes like Hubble captured this shift by studying distant supernovae, their light stretched and dimmed by the accelerating space between us and them. The discovery earned a Nobel Prize, not just because it revealed dark energy's existence, but because it rewrote our understanding of the universe's fate. The consequences are staggering. As dark energy stretches the cosmic web, galaxies tethered by gravity today will one day find their bonds broken. First, the most distant galaxies will vanish beyond an invisible horizon, their light stretched to wavelengths we can no longer detect. Later, even nearby galaxy clusters will be pulled apart, their member galaxies drifting into isolation. In 1 trillion years, the local group, our Milky Way, Andromeda, and their satellites might be the only galaxies left in our observable universe, an island in an ever-darkening sea. But dark energy's influence isn't uniform. Voids, already the emptiest regions of space, expand faster than dense galaxy clusters, amplifying the universe's contrasts. The cosmic web, once a tight-knit tapestry, will fray into thinning threads with galaxies stranded like shipwrecks on shrinking rafts of matter. Even black holes, the last remnants of galactic cores, won't escape. Over incomprehensible timescales, they'll evaporate via Hawking radiation, leaving behind a cold, dark expanse where not even light remains. Yet for all its destructive potential, dark energy might also be a creative force. Some theories suggest it could trigger new big bangs in far future epochs, birthing fresh universes in a cycle of cosmic renewal. Others propose it's not a constant at all, but a field that could decay or shift, potentially reversing its effects. For now, dark energy remains one of physics' greatest mysteries, an invisible hand guiding the universe toward an uncertain destiny. Every galaxy we study, every supernova we measure, brings us closer to understanding this force that doesn't just shape space, but time itself. The universe's story isn't ending. It's being rewritten by something we can't see, can't touch, and are only beginning to comprehend. Some galaxies defy every expectation. They're as wide as the Milky Way, but glow with the faintness of a candle glimpsed through fog. These are ultra-diffuse galaxies, the universe's ghostly enigmas, where stars are so sparse you could fly through one for light years without spotting a single sun. Imagine a galaxy where the night sky would appear nearly black, its handful of stars scattered like distant campfires across an unimaginable void. Yet despite their ghostly appearance, these galaxies are teaching us some of the most surprising lessons about how galaxies live, die, and sometimes fade into the shadows. Take Dragonfly 44, a galaxy in the Coma cluster. It spans 60,000 light-years, comparable to our Milky Way, but contains just 1% of its stars. At first glance, it shouldn't exist. With so few stars, its gravity shouldn't be strong enough to hold it together. Yet there it is, stubbornly intact. The secret: dark matter. Observations reveal this galaxy is wrapped in an enormous halo of invisible matter, 99% of its mass hidden in the shadows. This makes ultra-diffuse galaxies like Dragonfly 44 cosmic paradoxes, enormous yet faint, fragile looking yet bound by unseen forces. Then there's the question of their origins. Some might be failed galaxies, clumps of gas that started forming stars but stalled, their growth stunted by harsh environments like galaxy clusters, where hot plasma strips away their fuel. Others could be the shredded remains of violent collisions, their stars flung wide by ancient encounters. In the Virgo cluster, galaxies like VCC 1287 show faint, elongated shapes, as if stretched by gravitational tides long ago. These galactic ghosts might be the survivors of cosmic demolition derbies, their stars scattered but never lost. What's truly astonishing is how many of them exist. Telescopes like the Subaru Observatory have uncovered hundreds in just a single cluster, suggesting they've been hiding in plain sight all along. Their dimness made them nearly invisible to older surveys, but modern instruments are peeling back the layers of the night sky, revealing a hidden population of galaxies we never knew were there. Some, like the recently discovered dark galaxy Antlia 2, lurk right in our cosmic backyard, challenging assumptions about how galaxies form and evolve. Yet the biggest mystery isn't just how these galaxies exist, it's what they tell us about dark matter. Their sheer size and faintness make them perfect laboratories for studying this elusive substance. By measuring how stars move within them, astronomers can map the distribution of dark matter with unprecedented precision. Some ultra-diffuse galaxies even appear to lack dark matter entirely, like NGC 1052DF2, a finding that sparked debates and forced scientists to revisit their theories. Could these galaxies be the key to unlocking dark matter's secrets, or are they showing us that our understanding of gravity itself needs rewriting? Ultra-diffuse galaxies remind us that the universe still holds surprises in its quietest corners. They're proof that galaxies don't always blaze with starry brilliance. Sometimes they whisper, their stories written in faint light and invisible mass. Every new discovery peels back another layer of their mystery, revealing not just how galaxies fade, but how they endure against all odds. In their silence, they speak volumes about the hidden forces shaping the cosmos. Among the universe's most striking oddities are ring galaxies, cosmic bullseyes so perfectly shaped they seem almost artificial. These rare celestial structures, where a brilliant circle of young stars surrounds an older central core, defy the typical spiral or elliptical forms we associate with galaxies. The secret to their striking appearance, a high-speed galactic collision where one galaxy punches straight through the heart of another like a bullet through a target, sending shock waves rippling through the disk and triggering a fireworks display of star formation. Take the Cartwheel Galaxy, one of the most spectacular examples. Located 500 million light-years away, its vibrant blue ring spans 150,000 light-years, dotted with colossal star clusters and glowing nebulae. At its center lies a quieter, yellower core, the remnant of the original spiral galaxy that once existed before a smaller companion galaxy barreled through it nearly 300 million years ago. The impact sent waves of gas rushing outward, compressing it into a ring where millions of new stars ignited almost simultaneously. What makes the Cartwheel so mesmerizing isn't just its symmetry, but the way it captures a single, violent moment frozen in cosmic time, a snapshot of chaos transformed into art. But ring galaxies aren't just pretty accidents, they're natural laboratories for studying galactic physics. The expanding ring acts like a petri dish, allowing astronomers to observe how shockwaves propagate through interstellar gas and how star formation unfolds under extreme conditions. In the Cartwheel's case, the ring's outer edge is still ablaze with newborn stars, while the inner regions show slightly older stellar populations, a timeline of star birth written in light. These galaxies also reveal how quickly galactic structures can change. Unlike the slow, steady evolution of spirals, rings are fleeting phenomena. Within a few 100 million years, the Cartwheel's perfect circle will dissolve as the ring stars disperse or exhaust their gas, leaving behind a more amorphous shape. Not all ring galaxies form the same way. Some, like Hoag's object, defy the collision explanation. With its nearly flawless ring encircling a golden core, Hoag's appears too pristine to result from a violent encounter. Instead, astronomers suspect it might have formed through a rare instability in the galaxy's own disk, or perhaps from a long-ago interaction that's left no other visible traces. This mystery reminds us that even the most seemingly straightforward cosmic phenomena can harbor surprises, challenging our assumptions about how galaxies grow and change. What unites all ring galaxies is their ability to captivate. Whether born from catastrophic collisions or enigmatic internal processes, they stand as proof that the universe has a flair for the dramatic turning destruction into beauty, chaos into order. Every time we spot one of these cosmic bullseyes, we're reminded that galaxies aren't static paintings but dynamic, evolving entities, where even the most violent events can create something breathtaking. The next time you see an image of the cartwheel or Hoag's object, pause for a moment. You're not just looking at a galaxy, you're witnessing a masterpiece written in starlight, a fleeting moment of cosmic perfection. Imagine sitting at your computer, sipping coffee, and suddenly spotting a galaxy no scientist has ever studied before. That's the magic of Galaxy Zoo, a groundbreaking project that turns everyday people into cosmic explorers. With just an internet connection and curiosity, volunteers from around the globe help astronomers sift through millions of galaxy images, identifying odd shapes, rare mergers, and celestial anomalies that even advanced algorithms might miss. This isn't just busy work, it's real science where a teacher in Tokyo or a retiree in Buenos Aires could be the first to flag a galaxy with a never-before-seen structure. The premise is beautifully simple. Participants are shown images from telescopes like Hubble or the Sloan Digital Sky Survey and asked basic questions. Is this galaxy spiral or elliptical? Are there signs of collision? Does it have unusual features? What makes this so powerful is the human brain's knack for pattern recognition, something we still do better than computers, especially when it comes to spotting the unexpected. In one famous case, a Dutch schoolteacher named Hanny van Arkel discovered a bizarre green object lurking behind a galaxy. Dubbed Hanny's voorwerp, Dutch for Hanny's object, this enigmatic cloud turned out to be a cosmic ghost, a glowing echo of a quasar's past outburst, visible only because of its unique orientation. Without citizen scientists, it might have been overlooked entirely. But Galaxy Zoo's impact goes beyond serendipitous discoveries. By distributing the workload across thousands of eyes, researchers can analyze data at unprecedented speed. When the project launched in 2007, its first dataset, nearly 1 million galaxies, was classified in just 175 days, with professional astronomers that would have taken years. This collective effort has led to the identification of rare galaxy types, like red spirals, spinning disks with oddly dormant star formation, and blue ellipticals, aging galaxies suddenly reignited by fresh gas. Each classification helps piece together the puzzle of galactic evolution, revealing how environment, collisions, and internal dynamics shape a galaxy's fate. What's equally remarkable is how Galaxy Zoo fosters connection. Participants aren't just clicking buttons, they're joining forums, discussing their findings, and even co-authoring scientific papers. Over 50 publications have credited citizen scientists as contributors, proving this isn't just crowdsourcing, it's community. For many volunteers, the project becomes a gateway to deeper engagement with astronomy. Whether through follow-up projects like Radio Galaxy, Zoo mapping black hole jets, or Zooniverse's expanding suite of citizen science initiatives. At its core, Galaxy Zoo democratizes discovery. It proves that you don't need a PhD to advance our understanding of the cosmos, just a willingness to look closely and wonder. In an era where telescopes generate more data than professionals can possibly analyze alone, projects like this redefine who gets to participate in science. Every classified galaxy, every curious question from a volunteer, adds another thread to the tapestry of cosmic knowledge. So the next time you gaze at a starry sky, remember, the universe isn't just for experts. Its secrets are there for anyone bold enough to search. Galactic collisions don't just destroy, they create. Amid the chaos of two galaxies tearing each other apart, something remarkable can emerge: tidal dwarf galaxies. These aren't your typical dwarfs born from the primordial gas of the early universe. Instead, they're cosmic phoenixes, forged in the fiery aftermath of galactic encounters. Picture two spirals locked in a gravitational dance, their swirling arms stretched into long, shimmering streams of stars and gas. Where these tidal tails intersect, gravity gathers the scattered material, compressing it into glowing knots that ignite with newborn stars. Voila, a brand new galaxy, born not from the void but from the wreckage of its predecessors. What makes tidal dwarfs so fascinating is their composition. Unlike ancient dwarf galaxies, which are metal-poor relics from the universe's youth, these newcomers are rich in heavy elements: carbon, oxygen, iron, forged in the hearts of their parent galaxy stars. They're like cosmic recycling centers, turning the debris of destruction into something new and vibrant. Take NGC 7252's ARP-292, a tidal dwarf forming right now in the wake of a galactic collision. Its gas is laced with metals, and its young stars blaze with a blue-white intensity rare in older, more isolated dwarfs. Yet tidal dwarfs face an uphill battle. Without the protective halo of dark matter that shelters primordial dwarfs, they're fragile, held together only by the gravity of their visible stars and gas. Some may dissipate back into the void, their stars rejoining the tidal streams from which they came. Others, like the prolific dwarfs around the antennae galaxies, could endure for billions of years, becoming permanent fixtures of their galactic neighborhood. Their very existence challenges how we define a galaxy. Are they true galaxies or just temporary stellar clumps? The debate rages on, but one thing's clear: tidal dwarfs are proof that the universe thrives on creative destruction. Every time galaxies collide, they don't just reshape each other, they sow the seeds for new cosmic communities, turning chaos into cradle. So the next time you see an image of colliding galaxies, look closer. Those glowing knots in their tidal tails aren't just debris, they're the next generation of galaxies writing their first chapter in the stars. Galaxies aren't just factories for making stars, they're master recyclers, running cosmic salvage operations on a scale we're only beginning to understand. Picture this: a massive star reaches the end of its life and explodes as a supernova, blasting its outer layers into space at millions of miles per hour. But that gas doesn't just vanish into the void. Instead, it shoots up like a geyser, soaring hundreds or even thousands of light years above the galactic disk before gravity eventually pulls it back down in a shimmering rain of raw material. This isn't destruction, it's renewal, a process astronomers poetically call the Galactic Fountain. The mechanics are breathtaking. When superheated gas from multiple supernovae combines, it creates colossal bubbles in the interstellar medium, rising through the galaxy's magnetic fields like balloons through honey. Some of this material gets so far out it joins the galaxy's halo, that vast, sparse sphere of gas, dust, and dark matter surrounding the visible disk. There, in the relative quiet far from the crowded galactic plane, the gas has time to cool, condense, and turn into molecular clouds. Then, over millions of years, these clouds succumb to gravity's pull, cascading back down in graceful arcs to replenish the star-forming regions below. It's a celestial water cycle where instead of evaporation and rainfall, you have supernova and infall. The Milky Way's own fountain is hard at work right now. Near our galaxy's center, the Fermi bubble's twin lobes of hot gas stretching 25,000 light-years above and below the disk are likely fossil evidence of past fountain activity, powered by either a burst of supernova or a feeding frenzy from Sagittarius, a star. Meanwhile, observations with radio telescopes reveal cold, dense clouds high in the halo, some already falling back at speeds over 100 kilometers per second. These aren't static structures but dynamic rivers of rebirth, carrying the ingredients for new stars back to where they're needed most. What makes galactic fountains so vital is their role as regulators. Without them, galaxies would face a crisis, either burning through their gas too quickly in frenzied starbursts, or locking it away in old stars and stellar remnants forever. The fountain's delicate balance ensures a steady, sustainable pace of star formation. Too vigorous, and the gas gets blown entirely out of the galaxy, starving future generations of stars. Too weak, and the galaxy stagnates, its potential trapped in unused reservoirs. Our own solar system likely owes its existence to this recycling program, with many of its elements forged in stars whose remains were swept up in an ancient fountain's flow. Yet these fountains aren't perfect. Some gas escapes entirely, especially in smaller galaxies where gravity's grip is weaker. Others, like those in starburst galaxies, run too hot, their outflows so powerful they risk quenching star formation entirely. Even in the Milky Way, the efficiency isn't 100%. Some material gets lost to the intergalactic medium, a slow leak in the cosmic plumbing. But that's part of a grander cycle too, as this expelled gas may one day fuel neighboring galaxies or even future generations of cosmic structures we can't yet imagine. The next time you look up at the Milky Way's starry band, remember, you're not just seeing points of light. You're witnessing an intricate dance of creation and renewal, where death feeds birth across scales so vast they humble the imagination. Galactic fountains remind us that even in the cold depths of space, nothing is truly wasted. Every atom has its role to play in the unending story of stellar evolution. Something invisible is tugging at our galaxy, an unseen force so powerful it's pulling not just the Milky Way, but thousands of other galaxies toward a single point in space like moths to a flame. Astronomers call it the Great Attractor, and it's one of the universe's most tantalizing mysteries. Located about 250 million light-years away in the direction of the constellation Centaurus, this gravitational anomaly exerts an influence so vast that entire galaxy clusters are streaming toward it in a slow-motion river of stars. But here's the catch: we can't see it. The Great Attractor lies hidden behind the thick dust and stars of our own galaxy's disk, shrouded in a celestial blind spot that's frustrated astronomers for decades. What makes this cosmic tug-of-war so puzzling isn't just its strength, it's the sheer scale of what's involved. The Great Attractor's pull suggests a mass equivalent to tens of thousands of Milky Ways concentrated in one region, yet traditional observations reveal no obvious concentration of galaxies or galaxy clusters large enough to explain it. Early theories proposed it might be a supercluster, a dense knot of galaxies like the nearby Laniakea supercluster, which includes our Milky Way. But even Laniakea's combined mass falls short of accounting for the gravitational force at work. This discrepancy has led scientists to consider even grander possibilities: vast concentrations of dark matter, unseen galaxy clusters obscured by interstellar dust, or even structures so large they redefine our understanding of cosmic architecture. One clue lies in the peculiar motions of galaxies. Since the 1970s, astronomers have noticed that galaxies in our local universe aren't just drifting apart with the expansion of space, they're also flowing en masse toward this mysterious focal point. This phenomenon, dubbed dark flow, suggests the Great Attractor might not be the final destination, but merely a waypoint in an even larger cosmic current. Some researchers speculate the true source could lie beyond, in an immense structure like the Shapley supercluster, a staggering collection of galaxy clusters over 650 million light-years away. Others wonder if the Great Attractor is part of a web-like filament of dark matter, one of the universe's hidden highways guiding galaxies into alignment. The challenge of studying it is as daunting as the mystery itself. Peering through the Milky Way's crowded central plane is like trying to spot a distant lighthouse through a blizzard. Traditional optical telescopes struggle, but newer tools are cutting through the noise. Infrared observatories like the now-retired Herschel Space Agency have pierced the dust veil, revealing galaxies previously hidden in the zone of avoidance, the region of sky obscured by our own galaxy's bulk. Radio telescopes, particularly those mapping hydrogen gas, have also uncovered strange concentrations of matter in the Great Attractor's direction, hinting at massive structures lurking just out of view. The next generation of telescopes promises to pull back the curtain further. The square-kilometer array, with its unprecedented sensitivity to radio waves, could map the distribution of galaxies behind the Milky Way in exquisite detail. Meanwhile, ESA's Euclid mission, designed to study dark matter and dark energy, might indirectly reveal the Great Attractor's influence by tracing how it warps the paths of distant galaxies. Every new dataset brings us closer to understanding whether this cosmic enigma is a singular anomaly or a signpost pointing to even larger, unseen forces shaping the universe's grand design. What's at stake isn't just the identity of one gravitational oddity, it's our grasp of the cosmos's large-scale structure. If the Great Attractor turns out to be something entirely new, it could rewrite our models of how matter clusters across the universe. Or perhaps it's a reminder of how much we still don't see, a testament to the limits of our current tools in a universe where the most powerful forces might still be hiding in plain sight. Until we solve its riddle, the Great Attractor remains a humbling reminder. Even in an age of cosmic discovery, the universe still holds cards close to its chest. Hidden beneath the visible glow of stars and gas, an invisible force weaves through every galaxy threads of magnetism so subtle they're easy to overlook, yet powerful enough to shape galactic destiny. These magnetic fields might be 1,000,000 times weaker than a fridge magnet, but they stretch across tens of thousands of light-years, intertwining with spiral arms, looping around supernova remnants, and even guiding the flow of interstellar gas. Imagine them as cosmic spider silk, nearly weightless but strong enough to influence how galaxies breathe, spin, and give birth to new stars. How do such delicate forces leave their mark? Start with a spiral galaxy like our Milky Way. As it rotates, charged particles, electrons and ions move through its gas clouds, generating electric currents that spawn magnetic fields in return. Turbulence from supernova or stellar winds then twists and amplifies these fields, stretching them into chaotic filaments or organizing them into vast, coherent patterns. In some galaxies, like the nearby Whirlpool Galaxy, radio telescope observations reveal magnetic fields perfectly aligned with spiral arms, as if the galaxy itself is tracing invisible blueprints in the void. But magnetic fields don't just decorate galaxies, they sculpt them. Take star formation. Dense gas clouds need to collapse under gravity to ignite new stars, but magnetic pressure can resist that collapse, acting like an invisible cushion. Only when turbulence or shockwaves overpower the magnetic grip can gas fragment into stellar nurseries. This delicate tug of war explains why some galaxies, like the starbursting Messier 82, churn out stars at breakneck speeds. Their magnetic fields have been overwhelmed by violent galactic winds, unleashing a frenzy of star birth. The real surprise, these fields aren't static. They evolve alongside their galaxies, fossilizing past events like cosmic tape recorders. When a supernova explodes, its shockwave compresses nearby magnetic fields, leaving behind polarized imprints detectable by radio telescopes. In galaxy clusters, magnetic fields even thread the scorching gas between galaxies, betraying ancient collisions or jets from long, quiet black holes. The Virgo cluster, for instance, hosts magnetic structures so vast they defy explanation, perhaps relics of primordial fields from the universe's infancy. Yet mapping these invisible forces is like trying to photograph the wind. Astronomers rely on subtle clues, the way cosmic dust grains align with magnetic field lines, polarizing starlight, or how electrons spiraling around fields emit synchrotron radiation, a telltale radio glow. New tools like the Square Kilometer Array promise to reveal galactic magnetism in unprecedented detail, peeling back layers of history encoded in field strengths and orientations. What's at stake isn't just academic curiosity. Without accounting for magnetic fields, our models of galaxy evolution are incomplete, like forecasting weather while ignoring wind. They govern how gas cools, how cosmic rays propagate, even how galaxies interact with their surroundings. In the grand tapestry of the cosmos, magnetism is the silent weaver, its threads binding together everything from the smallest gas clouds to the largest galactic clusters. So the next time you gaze at a galaxy's luminous spiral, remember, there's more to its story than meets the eye, written not in starlight, but in the whispers of invisible forces. Imagine a galaxy as a vast metropolis, some neighborhoods teeming with activity, others eerily quiet, and only a select few offering the perfect conditions for life to flourish. This is the concept of galactic habitable zones, regions where the delicate balance of safety, resources, and stability align to make life possible. Just as Earth orbits within our solar system's habitable zone, where liquid water can exist, our solar system itself sits within a privileged annular band of the Milky Way, where the cosmic environment isn't too harsh nor too barren, but just right. Venture too close to the galactic center and the challenges mount. Here, stars pack together tightly, their gravitational dances stirring up chaos. Supernova explode with frightening frequency, bathing nearby space in lethal radiation. The supermassive black hole at the Milky Way's heart, Sagittarius A star, occasionally awakens, spewing X-rays and gamma rays that could sterilize entire planetary systems. Even without these cataclysms, the sheer density of stars increases the risk of deadly encounters, asteroids or comets hurled toward planets by passing gravitational perturbations. It's a cosmic equivalent of living near an active volcano, thrilling but hardly conducive to long-term survival. On the other hand, the galaxy's outer reaches present a different problem. Here, stars are few and far between, and the interstellar medium is thinly spread. That scarcity extends to heavy elements like iron, silicon, and oxygen, the building blocks of rocky planets and organic molecules. Without enough of these materials, planetary systems may lack the diversity needed to sustain complex chemistry, let alone life. It's like trying to build a thriving city in a desert with no raw materials, possible but far from ideal. So where's the sweet spot for the Milky Way? It's a ring-shaped region about 25,000 light-years from the center, spanning a few thousand light-years in width. This annulus avoids the inner galaxy's radiation frenzy while still benefiting from its richer metallicity. Our Sun orbits comfortably within this zone, about 27,000 light-years out, in a relatively quiet spiral arm spur. Crucially, this region also offers stability. The Sun's circular orbit keeps it safely distanced from the crowded inner disk, while the Milky Way's barred spiral structure funnels gas and stars in ways that may periodically replenish star-forming materials without overwhelming the neighborhood. Timing matters as much as location. The Milky Way's early epochs were turbulent, with frequent supernova and mergers. Only after the galaxy matured around 5 to 6 billion years ago did conditions calm enough for stable, long-lived planetary systems to emerge. By the time Earth formed 4.5 billion years ago, the galaxy had settled into a relatively quiet middle age with fewer catastrophic disruptions. But habitability isn't just about avoiding disaster, it's also about opportunity. The galactic habitable zone ensures planets have access to the right mix of elements, the right amount of energy, and enough time for life to evolve. It's a reminder that we're not just lucky to be on a hospitable planet, but in a hospitable part of a galaxy where the cosmos itself conspires to make life possible. Every time we scan the night sky for exoplanets, we're subconsciously searching for other worlds nestled in their own galactic Goldilocks zones, wondering if the universe has written the same recipe for life elsewhere. Think of galaxies as cosmic dynasties. Their wealth, power, and longevity all hinge on one critical factor: mass. This isn't just about size, it's about gravitational influence, the ability to attract and retain resources, and ultimately, the capacity to shape their own destinies. A galaxy's mass acts like a cosmic bank account, determining whether it becomes a dominant force in the universe or gets swallowed by larger neighbors. The Milky Way, for instance, sits comfortably in the middle class, massive enough to host dozens of satellite galaxies, but nowhere near the scale of true giants like Messier 87, which weighs as much as 200 Milky Ways and reigns supreme at the heart of the Virgo cluster. At the top of this hierarchy, supermassive galaxies grow through relentless mergers. Picture two spiral galaxies colliding, their delicate structures shredded, their gas compressed into frenzied starbursts, their central black holes eventually spiraling together in a gravitational tango. The result, a monstrous elliptical galaxy, its stars orbiting in chaotic swarms rather than neat disks. These galactic titans often anchor galaxy clusters, their immense gravity dictating the motion of thousands of smaller galaxies. The more they consume, the more they attract, creating a feedback loop of growth. Take the Phoenix Cluster's central galaxy. It's not just growing, it's gorging on gas at a rate of 280 solar masses per year, birthing new stars in quantities that defy conventional wisdom. Smaller galaxies face a far grimmer fate. Dwarfs like the Large Magellanic Cloud may shine brightly, but without enough mass to hold onto their gas or resist tidal forces, they're destined to be torn apart. The Milky Way's halo is littered with stellar streams, the ghostly remnants of dwarfs consumed over billions of years. Even more isolated small galaxies aren't safe. In clusters like Coma, the hot intergalactic medium acts like a cosmic blowtorch, stripping gas from infalling dwarfs in a process called ram pressure stripping. Deprived of star-forming fuel, these galaxies fade into obscurity, their stellar populations aging into reddish hues while their heavier elements are recycled into the cluster's ecosystem. Mass also dictates a galaxy's internal dynamics. The heftiest galaxies host the most active supermassive black holes, their gravity funneling gas toward the center at staggering rates. This isn't a gentle process. The infalling material heats up, glowing brilliantly as quasars or blasting out jets that can sterilize entire galaxies of star-forming gas. Meanwhile, lower mass galaxies like our own maintain a quieter equilibrium, their black holes feeding just enough to regulate star formation without triggering self-destructive outbursts. Yet the most profound consequence of galactic mass might be its imprint on the cosmic web. Massive galaxies cluster along dark matter filaments, their gravity bending the very structure of space around them. Smaller galaxies flow toward these nodes like tributaries into a river, their paths tracing the invisible scaffolding of the universe. This isn't random. It's a meticulously orchestrated dance where mass writes the music, and everything else follows its rhythm. So the next time you gaze at a galaxy, remember, you're not just seeing a collection of stars, you're witnessing the outcome of a cosmic balancing act, where mass determines whether a galaxy thrives, survives, or vanishes entirely. From the tiniest dwarfs to the most colossal cluster dominators, each one tells a story of gravitational triumph or defeat. In the early 20th century, Edwin Hubble peered through the eyepiece of the Hooker telescope and saw more than just swirling masses of stars. He saw patterns, a cosmic taxonomy waiting to be deciphered. His solution, the tuning fork diagram, a simple yet revolutionary way to classify galaxies by their shapes. Picture a literal tuning fork. On the left, elliptical galaxies, smooth and featureless, graded by how stretched or round they appear. Along the right prong, spirals branch into two paths, those with a central bar of stars, and those without, each arm winding tighter or looser like variations on a celestial melody. And at the base, irregular galaxies, the misfits that refuse to conform. At first glance, Hubble's system seems almost too neat. After all, galaxies are chaotic, evolving beasts, shaped by collisions, star formation, and the invisible hand of dark matter. Yet that simplicity is precisely what made it enduring. By focusing on visible structure, the tuning fork gave astronomers a common language, a way to quickly categorize the thousands of galaxies flooding observatory archives. Take Messier 87, the giant elliptical in Virgo. Its smooth, golden glow slots perfectly into the E0 category, denoting near-perfect roundness. Meanwhile, the Whirlpool Galaxy, with its two sweeping arms, is a textbook SC, a spiral without a bar and loosely wound. But Hubble himself knew this was just the first draft of a much richer story. Modern telescopes have since revealed galaxies that defy his categories, like ultra-diffuse galaxies, so ghostly they're barely visible, or ring galaxies like Hoag's object, where stars form a perfect circle with nothing but emptiness in between. Even the classic spirals and ellipticals harbor surprises. Some spirals, dubbed red and dead, have stopped forming stars entirely, their arms frozen in time. Certain ellipticals, thought to be quiet retirement homes for aging stars, hide reservoirs of cold gas, hinting at past mergers or secret rebirths. The Hubble sequence's true legacy isn't in its limits, but in how it set the stage for deeper questions. Why do spirals dominate the cosmic countryside while ellipticals cluster in crowded metropolises like galaxy clusters? How do bars, those straight lines of stars cutting through spiral cores, shape a galaxy's evolution? The tuning fork didn't just classify galaxies, it framed the conversation, giving astronomers a scaffold to hang new discoveries on. Today, as telescopes like James Webb peer back to the universe's infancy, they're finding galaxies that look nothing like Hubble's class's clumpy, disorganized, and still figuring out their identities. These cosmic toddlers remind us that classification isn't about boxing nature in, but about recognizing the patterns that help us ask better questions. The Hubble sequence isn't a finished map, it's the starting point for a journey into how galaxies grow, change, and reveal the universe's hidden rules. Every time we slot a new galaxy into the tuning fork or stumble upon one that shatters it, we're not just labeling, we're learning to read the universe's handwriting. Supercomputers have become the ultimate time machines for astrophysicists, constructing entire virtual universes where galaxies form, collide, and evolve over billions of years, all inside the memory of a machine. These aren't just animations, they're precise mathematical experiments where every particle of dark matter, every wisp of gas, obeys the laws of physics as we understand them. Take the famous Illustris TNG project, a simulation so detailed it tracks the birth and death of millions of stars across a cube of space 300 million light-years wide. Within this digital cosmos, primordial gas clumps together under gravity's pull, igniting the first stars, while supernova blast heavy elements into the void, enriching future generations of galaxies. The result, a breathtakingly realistic cosmic tapestry that looks uncannily like the real universe we observe through telescopes. What makes these simulations revolutionary isn't just their scale, but their predictive power. When astronomers tweak variables adjusting the strength of supernova, winds, or the behavior of dark matter, the virtual galaxies respond in ways that either match or challenge our observations. For instance, early simulations struggled to explain why massive galaxies don't grow as large as theory suggested they should. The solution emerged when researchers added black hole feedback, the idea that supermassive black holes inject energy into their surroundings, heating gas and stifling star formation. Suddenly, the simulated galaxies matched their real counterparts, a eureka, a moment that reshaped our understanding of galactic growth. Yet simulations also reveal surprises no telescope could catch. In the Eagle project, a virtual galaxy spontaneously developed a barred spiral structure, a feature no programmer explicitly coded, but one that emerged naturally from the interplay of gravity and rotation. Other simulations have shown how cosmic filaments funnel gas into galaxies like rivers feeding a lake, or how dwarf galaxies orbiting the Milky Way might be debris from a single, ancient collision. These aren't just pretty visuals, they're testable hypotheses guiding astronomers to look for specific patterns in real data. The challenges are as daunting as the breakthroughs. Simulating even a single galaxy requires balancing absurdly different scales, from the parsec-wide chaos around black holes to the million light-year sweep of dark matter halos. Some models, like NAS, a Romulus C, tackle this by zooming in on individual galaxies while accounting for the gravitational tides of their cosmic neighborhood. Others, like the FIRE simulations, focus on the microphysics of star formation, capturing how radiation from young stars blows bubbles in surrounding gas, regulating future star birth. Each approach fills gaps in our knowledge, revealing how galaxies are shaped by forces both titanic and subtle. Perhaps the most humbling lesson from these virtual universes is how much we still don't know. When simulations disagree with observations, like predicting too many small galaxies or stars in the wrong places, it's not a failure but a clue. These discrepancies point to missing physics, perhaps in our models of dark matter, supernova explosions, or magnetic fields. Every mismatch is a breadcrumb leading to deeper truths, proving that galaxies aren't just islands of stars, but dynamic puzzles where every piece, from the tiniest particle to the largest structure, interlocks in ways we're only beginning to decode. So the next time you see a galaxy's majestic spiral or a cluster's golden glow, remember, behind that image lies an invisible framework of equations and algorithms, a digital universe where scientists test, fail, and try again, all to understand the cosmic story we're all a part of. Simulations don't just mimic reality, they're laboratories where the universe teaches us its secrets, one line of code at a time. At the heart of every massive galaxy, a paradox unfolds. Supermassive black holes, famed for their destructive appetites, are secretly master regulators, sculpting their galactic homes through explosive generosity. These cosmic behemoths don't just devour matter, they recycle it, transforming swallowed gas into colossal outflows of energy that ripple through their host galaxies like shockwaves from a dynamite blast. Picture a black hole feasting on a spiraling disk of superheated gas, only to belch out jets of plasma moving at near light speed, or radiate enough ultraviolet light to ionize entire nebulae. This isn't chaos, it's precision engineering on a galactic scale. Take the Perseus Cluster's central galaxy, where the black hole's jets have carved gargantuan bubbles in the surrounding hot gas, each cavity spanning tens of thousands of light years. These aren't empty voids but cosmic pressure valves, where the injected energy balances the gas's natural tendency to cool and collapse. Without these outbursts, the galaxy's core would flood with cold gas, igniting such rampant star formation that it would burn through its fuel reserves in a celestial frenzy. Instead, the black hole's feedback acts like a thermostat, turning the heat up just enough to prevent catastrophic cooling without boiling everything away. The mechanics of this balancing act are breathtakingly elegant. As gas falls toward the black hole, friction heats it to millions of degrees, causing some particles to escape as high-speed winds before crossing the event horizon. In other cases, magnetic fields coil like cosmic springs, launching focused jets that drill through interstellar space. These outflows do more than just stir the pot, they enrich the galaxy, seeding it with heavy elements forged in the black hole's violent vicinity. The Milky Way's own supermassive black hole, Sagittarius A star, may seem quiet now, but fossils in our galactic halo suggest it too had fiery outbursts in the past, its feedback helping shape the spiral we call home. What's astonishing is how tightly linked black hole activity is to galaxy-wide star formation. In galaxies like Messier 82, where stars are born at breakneck speeds, black hole feedback eventually blows away the gas supply, quenching the starburst like a cosmic fire hose dousing flames. Conversely, in aging ellipticals, the lack of fresh gas starves both the black hole and star formation, leaving a galaxy full of red giants and stellar remnants. This symbiotic relationship explains why we don't see galaxies with oversized black holes and runaway star formation, or galaxies with tiny black holes and no stars at all. The two are locked in a dance, each regulating the other across billions of years. Yet feedback isn't always gentle. In the early universe, quasars, the ultraluminous cores of young galaxies, blasted their surroundings with enough energy to strip gas from neighboring dwarfs, effectively sterilizing them. Some theorists argue this violent pruning helped establish the cosmic hierarchy we see today, where massive galaxies dominate while smaller ones orbit like satellites. Even now, astronomers find evidence of these ancient tempests in the chemical compositions of the oldest stars, their atmospheres bearing the scars of black hole winds that blew across the cosmos long before Earth formed. The lesson hidden in these galactic power struggles is profound. Destruction and creation are two sides of the same coin. Supermassive black holes, often cast as villains in the cosmic story, are in fact custodians, ensuring galaxies neither exhaust themselves in stellar bonfires nor fade into inert darkness. Their feedback loops are nature's way of enforcing balance, a reminder that even the most violent forces can give rise to order. Every time astronomers detect the faint glow of a distant quasar or map the ripples of an ancient jet, they're glimpsing the invisible hands that shape galaxies into the diverse, stable structures we marvel at today. Dwarf galaxies are the cosmic equivalent of small fish in a shark tank surrounded by giants, vulnerable to every gravitational current, yet somehow enduring against staggering odds. These galactic underdogs, some no larger than 1,000th the mass of the Milky Way, face a universe that's actively hostile to their survival. Picture a tiny, glowing smudge of stars drifting near a colossal spiral like Andromeda. Its fate hinges on a brutal calculus. Stray too close and tidal forces will stretch it into a stellar stream. Linger too far and it might wither away, starved of the gas needed to birth new stars. Yet within these struggles lies a revelation. Dwarf galaxies aren't just victims of cosmic forces. They're survivors, their stories etched in the scars they bear, and the rare pockets of space where they've carved out a tenuous existence. Take the Sagittarius dwarf spheroidal, one of the Milky Way's closest satellites. Once an independent galaxy, it's now being unraveled by our galaxy's gravity, its stars scattered into a shimmering arc that wraps around the Milky Way like a celestial ribbon. This slow-motion destruction isn't unique. Across the universe, dwarfs are the building blocks sacrificed to build giants, their stars assimilated into larger galaxies over billions of years. But not all meet this fate. Isolated dwarfs like the quirky Leo T, drifting in the void between galaxy clusters, cling to fragile autonomy. With just enough gas to spark occasional star formation, they're like cosmic hermits, eking out an existence far from the gravitational fray. What makes these tiny galaxies so revealing is their sensitivity to their environments. In dense galaxy clusters, dwarfs are stripped of their gas by the searing heat of intergalactic plasma, leaving them red and dead with no fuel for new stars. Yet in quieter corners of the universe, some dwarfs like the Wolf-Lundmark-Melot galaxy defy expectations, churning out stars despite their modest size. Their resilience hints at a hidden diversity. Some may be ancient relics from the universe's first billion years, while others could be the shredded remnants of larger galaxies, reshaped by violent encounters. Even their dark matter tells a story. Most dwarfs are thought to be cocooned in dense halos of this mysterious substance, which helps them withstand tidal forces. But oddballs like NGC 1052DF2, nearly devoid of dark matter, append assumptions about how galaxies form. Was it born this way, or did a collision rip its dark matter away? The answer could rewrite our understanding of galactic evolution. Dwarf galaxies remind us that the cosmos isn't just shaped by its giants. These small, often overlooked systems are the universe's most sensitive probes, reacting to every ripple in the gravitational landscape. Their struggles, whether ending in destruction, quiet endurance, or something in between, paint a vivid portrait of a cosmos where size isn't everything, but survival is never guaranteed. Every time astronomers spot a faint dwarf clinging to the edge of a cluster or drifting alone in the void, they're glimpsing the raw, unfiltered drama of galactic life on the smallest scale. Galaxies where their life stories in color, brilliant blues for vibrant youth, deep reds for quiet maturity, and every hue in between marking their place in the cosmic life cycle. The secret lies in their starlight. Young galaxies blaze with the blue-white intensity of massive, short-lived stars, each one burning fiercely at temperatures over 30,000 degrees. These stellar powerhouses dominate the light output, painting their galaxies in cool, electric tones, but their brilliance is fleeting. Within a few million years, they explode as supernova, leaving behind smaller, longer-lived stars that glow with the golden warmth of a setting sun. Over billions of years, as star formation slows and these aging stars come to dominate, the galaxy's color shifts first to yellow, then orange, and finally to the deep crimson of a celestial elder. The Whirlpool Galaxy offers a textbook example. Its spiral arms shimmer with the sapphire glow of newborn clusters, where dense gas clouds collapse into fresh generations of stars. Meanwhile, its central bulge glows gold, crowded with older stars that formed billions of years ago. This color gradient isn't just aesthetic, it's a timeline chronicling the galaxy's growth from the inside out. Even more extreme are starburst galaxies like Messier 82, where frenzied star formation bathes the entire system in a cobalt sheen, a temporary blaze of youth before the inevitable fade to red. Yet color doesn't just reflect age, it reveals environment. Galaxy clusters, those crowded cosmic cities, are dominated by red ellipticals. Here, the harsh realities of communal living take their toll. Hot gas between galaxies strips away the raw materials for new stars, while gravitational interactions disrupt delicate spiral structures. The result: a population of red and dead galaxies, their star-forming days long past. In contrast, the cosmic countryside, where galaxies drift in relative isolation, teems with blue spirals, their gas reservoirs intact, their stellar nurseries still bustling. There are exceptions, of course, and that's where things get fascinating. Some red galaxies hide secrets. Take red spirals, a rare breed that maintains its elegant arms despite a lack of star formation. These galaxies might have been cut off from fresh gas supplies, their spiral structure frozen in time like a photograph. Others, like rejuvenated ellipticals, briefly flicker back to blue after colliding with gas-rich neighbors, proving that even the oldest galaxies can experience second acts. The true power of galactic color lies in its ability to tell stories across cosmic distances. When astronomers peer deep into the universe, they're seeing galaxies as they were billions of years ago, and the farther they look, the bluer the galactic population becomes. This isn't a coincidence, it's evidence of a younger, more energetic universe, one where galaxies were still in their star-forming prime. Every hue in a galaxy's palette, from the piercing blue of a stellar nursery to the somber red of a retired giant, is a brushstroke in the grand portrait of cosmic evolution. So the next time you see an image of a galaxy, don't just admire its beauty, decode its colors. They're the universe's way of keeping a diary written in starlight. The Milky Way's past isn't locked away in some distant corner of the cosmos. It's written in the motions and positions of billions of stars swirling around us right now. And no tool has decoded this celestial archive more powerfully than the Gaia spacecraft, a European Space Agency mission that's essentially given astronomers X-ray vision into our galaxy's hidden anatomy. Since its launch in 2013, Gaia has meticulously charted the precise locations, distances, and velocities of nearly 2 billion stars, an unprecedented census that's turning our understanding of galactic history upside down. Imagine trying to reconstruct a city's entire history by tracking the movements of every resident over centuries. That's the scale of Gaia's ambition, except its subjects are stars, and its timeline spans billions of years. What makes Gaia revolutionary isn't just the sheer volume of data, it's the precision. By measuring stellar positions down to the equivalent of spotting a coin on the moon from Earth, Gaia detects subtle wobbles and drifts that betray a star's origins. Take the so-called Gaia sausage, a sprawling stream of stars orbiting the Milky Way's core at steep angles. Their unusual paths tell a violent story. They're the debris of a dwarf galaxy that smashed into the Milky Way nearly 10 billion years ago, an impact so colossal it likely shaped our galaxy's thick disk and triggered a frenzy of star formation. Without Gaia's ability to trace these stellar orbits in 3D, this ancient cataclysm might have remained forever hidden. But Gaia's revelations go beyond collisions. Its data has exposed stellar highways, vast rivers of stars flowing through the Milky Way's halo, each one the remnants of a smaller galaxy devoured long ago. Some, like the Helmi stream, are cosmic fossils, their stars moving in unison like a school of fish despite being scattered across thousands of light years. Others, like the Nix stream, hint at more recent mergers, their stars still bearing chemical signatures that link them to their original homes. It's as if Gaia has given us a time lapse of the Milky Way's growth, revealing how our galaxy evolved from a modest clump of gas into the sprawling spiral we see today, not in isolation, but through a relentless campaign of galactic conquest. The spacecraft's impact isn't limited to archaeology. By mapping the Milky Way's current structure in exquisite detail, Gaia has uncovered oddities that challenge textbook models. The galaxy's disk isn't flat but warped, like a vinyl record left in the sun, possibly due to past encounters with satellite galaxies. Nearby spiral arms show unexpected kinks and fractures, suggesting the Milky Way's serene appearance masks a turbulent history of gravitational disturbances. Even seemingly mundane stars have stories to tell. Gaia has identified blue stragglers, stars that appear younger than their surroundings, likely rejuvenated by stealing mass from companions or colliding with other stars. These outliers are cosmic rogues flouting the rules of stellar evolution. Perhaps Gaia's most profound contribution is how it bridges the past and future. By backtracking stellar motions, astronomers can rewind the galaxy's evolution, reconstructing mergers and migrations that occurred long before Earth formed. But Gaia also lets us fast forward, predicting future encounters. Its data confirms, for instance, that the Large Magellanic Cloud, a satellite galaxy once thought to orbit harmlessly, is on a collision course with the Milky Way, destined to merge with us in about 2.5 billion years. This isn't just about curiosity, it's about context. Every star Gaia maps is a data point in the Milky Way's ongoing autobiography, a reminder that galaxies aren't static museums but living, changing entities. The mission's legacy is still unfolding. With each data release, Gaia peels back another layer of our galaxy's history, turning what was once speculation into concrete evidence. It's a testament to how much we can learn by simply really looking at the stars around us. Every pinprick of light in the night sky carries a story, and thanks to Gaia, we're finally learning how to read them. Galaxies don't drift through the cosmos alone, they're woven into an immense, invisible tapestry, connected by threads of dark matter and gas that stretch across billions of light years. This is the cosmic web, the universe's grand infrastructure, where galaxies cluster like glittering beads strung along vast, intersecting filaments. Picture a spider's web on a dewy morning, each droplet of moisture clinging to the silk, except here, the droplets are galaxies, and the silk is the gravitational scaffolding of the universe itself. This web doesn't just arrange galaxies, it shapes their very existence, funneling them the raw materials they need to grow and determining their ultimate fate. At the heart of this structure lies dark matter, the unseen architect. Though invisible, its gravitational pull sculpts the web's filaments, drawing ordinary matter, hydrogen and helium gas, into these meandering rivers. Over time, gravity works its magic, pulling gas along the filaments like water flowing through a network of pipes. Where these streams intersect, galaxies and clusters form, fed by the constant supply of fresh material. It's a cosmic delivery system, ensuring that the universe's largest structures never run out of fuel. The Milky Way, for instance, sits at the intersection of several filaments, its spiral arms likely fed by streams of gas trickling in from this hidden network. The scale of these filaments is almost incomprehensible. Some span hundreds of millions of light years, threading through the void like bridges between islands of galaxies. The Sloan Great Wall, one of the largest known structures, stretches over 1.5 billion light years, a filament so vast it would take light, the fastest thing in the universe, nearly a tenth of cosmic history just to traverse it. And yet, despite their enormity, these filaments are surprisingly delicate. The gas within them is so diffuse that, if you stood inside one, you wouldn't even know it was there, just a few atoms per cubic meter, far emptier than the best vacuum we can create on Earth. Yet for all their subtlety, these filaments wield incredible power. Galaxies born along these cosmic highways grow faster and larger, nurtured by the steady stream of gas. Those stranded in the voids, the vast, empty regions between filaments, often remain small and stunted, their star formation stifled by isolation. Even the motion of galaxies is dictated by the web. They slide along these dark matter thoroughfares like cars on a freeway, pulled toward the densest clusters where gravity's grip is strongest. The Virgo cluster, our nearest galactic metropolis, owes its existence to this relentless flow, with thousands of galaxies drawn into its orbit over billions of years. But the cosmic web isn't static. It evolves over time, with filaments growing thicker as gravity pulls more matter into them, while the voids between them stretch ever larger. Computer simulations like Illustrious TNG show this process in stunning detail, filaments forming, merging, and reshaping the universe in an endless dance. And as telescopes like the James Webb Space Telescope peer deeper into the cosmos, they're capturing glimpses of this web in its infancy, when the universe was just a fraction of its current age. These observations reveal a startling truth. The web structure was already in place when the cosmos was young, its filaments acting as cosmic nurseries for the first galaxies. What makes this discovery so profound is how it reshapes our understanding of cosmic evolution. The web isn't just a backdrop, it's an active participant, guiding galaxies toward collisions, fueling their growth, and even determining their shapes. Spiral galaxies like our Milky Way thrive in quieter regions, where gas flows smoothly along filaments. Elliptical galaxies, by contrast, are born in the crowded junctions of the web, where violent mergers and relentless tides erase their delicate structures. Every galaxy story is in part a story of its place in the web, a reminder that the universe is anything but random. The cosmic web is more than a scientific curiosity. It's a window into the universe's deepest mysteries. By studying its structure, astronomers can trace the history of dark matter, map the flow of gas across cosmic time, and even predict where new galaxies will form. It's a reminder that, on the grandest scales, the universe is a tapestry of connections, where even the most distant galaxies are linked by invisible threads. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're seeing the knots in a vast, shimmering web, one that's been weaving itself together since the dawn of time. From the first flickers of starlight to the majestic spirals we see today, galaxies have undergone an extraordinary journey, one that's far from over. Each of these 40 cosmic milestones is a testament to the universe's relentless creativity, where chaos and order dance in perfect balance. Think about it, those primordial hydrogen clouds that collapsed into the first stars now live on in the oxygen you breathe, the iron in your blood, even the calcium in your bones. The universe didn't just build galaxies, it built us, recycling stardust across billions of years into something that can marvel back at its origins. But here's what's truly humbling. This story isn't locked in the past. Right now, galaxies are colliding, stars are being born, and black holes are shaping their surroundings in ways we're only beginning to understand. Telescopes like James Webb are pulling back the curtain on cosmic dawn, capturing light from galaxies so young they haven't even settled into their final forms. Meanwhile, simulations are revealing how dark matter weaves the cosmic web, guiding galaxies into clusters and filaments with invisible hands. every discovery peels back another layer, showing us that the universe is richer, stranger, and more interconnected than we ever imagined. And yet, for all we've learned, the mysteries only deepen. What sparked the epoch of re-ionization? How do supermassive black holes and their host galaxies communicate so precisely? Why do some galaxies flicker out while others burn bright for eons? These questions aren't just academic, they're threads in a tapestry that connects the quantum to the cosmic, the infinitesimal to the infinite. So the next time you step outside and look up, remember, you're not just an observer of this grand saga. You're a participant, a living fragment of the universe's autobiography. Those pinpricks of light aren't static decorations, they're chapters in a story that's still being written, one where gravity, time, and wonder conspire to create something greater than the sum of its parts. The night sky isn't a ceiling. It's an invitation to explore, to question, and to carry forward the curiosity that's guided us from the first stargazers to the cutting-edge labs of today. The cosmos doesn't just belong to astronomers, it belongs to anyone who's ever looked up and felt that timeless pull toward the unknown. Keep chasing it. The next milestone is out there.